All right, so we're all set. So today what we're going to do, well, what we've done so far is that we understand the notion of the idea of distributions. We have a really good idea about these, right? That was very important to understand what a distribution is. The reason we need to understand the concept of a distribution is that whenever we have a parameter, call it theta, we're going to have some prior on that parameter, right? And this prior is a probability density function usually. So we need to have a pretty good idea of what we are talking about when we define a prior. And one of the key things I try to show you in this course is that whenever you are thinking about a prior for your own research problem, you need to try to visualize it graphically. And I showed you many times how to do that, with d beta, d norm, and so on, right? All these functions, they allow you to visualize your prior. And this gives you a very good understanding of what the belief amounts to, about that parameter. We will look at this concept in more detail now, okay? All right, so the other thing we learned was how to deal with some conjugate forms. Conjugate forms, and we saw two classical examples, right? We saw the beta binomial yesterday, and we saw, what was the other one? The Poisson gamma, right? And so these two examples, and in the homework, there were some more. I think there was an exponential gamma. And I think, so there are many other conjugate forms that I didn't discuss. There's also the normal prior, normal likelihood. And that's also a conjugate form. So there are many other examples like this. But these conjugate forms, I mean, they only serve one purpose for us in the 21st century. The purpose that they serve is that they allow us to get a really good understanding of what it means to multiply a likelihood with a prior analytically, just on paper, right? So that's good to know. Why? Because as I showed you yesterday with the Poisson gamma, you can really understand why the posterior mean is a compromise between the prior mean and the maximum likelihood estimate. It's a weighted mean. I proved that for you in the Poisson gamma case. The reason I chose the Poisson gamma to prove this was that it's an easy proof. I could have proved it with the normal conjugate form, but this is a very complicated proof, right? It requires serious algebra, to do that. And so that's why I chose a simple example. But the point is that in all conjugate forms, it will always be the case that the posterior mean is a weighted mean of the prior mean and the maximum likelihood estimate. So this is all very well, but this is not the kind of analysis that we'll do in real life, because in real life, we will have linear mixed models. We'll have repeated measures data. So today I'm going to start building up towards that. And in order to get to the linear mixed model, I'm going to have to start with the simple regression model, the simple linear model type of framework. So that's where I'm going now. Okay, so that's what the, oh no, this is the wrong wrong slides here. I'm showing you yesterday's slides, right? These are, yeah. So I don't know how I ended up with these slides. So let me see if I can fix this.
You have to click the green button again to undo the whole thing.
Well, if I can find the green button now.
Okay, then just press escape and you'll be out of it.
No, I'm not out of it. Hey, you got me stuck here. So I have to stop sharing probably. That's probably what's happening. Sorry, I'll just get back to this. I'm sorry about that. I'm totally incompetent with this stuff right now. So. But I will get there. I will get there. Let's try it again. And this will be to the left of screen. And then to the right of the screen will be mine, which we call it. Hey, Paula, what's going to happen if I want my RStudio back now? It's not going to be possible, right?
Usually either I click the green button again or escape and then I'm back to my normal screen. It could happen to you too. Or you
Okay.
could, if you want to use your RStudio, what you could do is using command and the arrow, you know, like when you change the screens, you know what I'm talking about? And then select RStudio and it pops out. And then you can come back to a double screen automatically, easily.
Well, let's see. I mean, how hard can this be? So I don't know what's happening now. So I'm like, sorry, I've messed up everything. Just a minute. I don't know what I've done wrong here. Just give me a second, guys. I don't know. We are wasting time on this now. It's not good. Full screen. Why is that? Yeah, this should work now. Wow, so annoying. Okay, for now, I'm going to stay with what I have here, right? So regression modeling, you can see this now, right? Yes? Okay. So what we are going to talk about today is a simple linear modeling situation where I've got a vector of independent and identically distributed data. So in statistics, we write it like this: y tilde, and then the likelihood function that is assumed to generate the data. And on top of that, on top of the tilde, I've written IID. And this is meant to indicate that every data point in this vector is independent and identically distributed. That means that it comes from this distribution with one mean and one standard deviation. Mu and sigma are the parameters of interest here, and these are unknown values. We will never know what these true values are. Just remember that. However, what we will do is that we will pretend that we know what these values are. We will generate fake data from this likelihood function, right? From this dnorm or what is it, rnorm function, right? And that way, in that way, we can study the properties of the model that we will fit. What's the model that we'll fit? It's this model here. This is the familiar way in which you see this model stated, right? So y is being produced from some average reading time and some Gaussian noise, right? And the Gaussian noise is assumed to have some standard deviation sigma and some mean 0, right? So this is your familiar model that you must have seen in your in your textbooks in psychology and so on, right? So, but the way we are going to write it is like this. We are going to assume a normal likelihood. There will be some sigma and some mu here, right? So these are two identical ways to write the same model. So don't be confused about this, okay? Right. So we have two parameters, mu and sigma. So we're going to have to define some priors on these. So if you look here, right, we've got mu and we got sigma, and we're going to have to decide what priors to use on these, right? That's what those tildes are for. So that's where I'm going with this next, right? So if you remember, what we are going to do in Bayesian modeling is that we are always given some data. We always start with some data, just like always. We're going to specify a likelihood function. This is a subjective choice that you are making. The likelihood function you are choosing is a subjective decision. So frequentists like to criticize Bayesian methods, saying that frequentist methods are objective. But the first thing that they do is they make a subjective choice about the likelihood function. The Elmer function forces you to choose the normal likelihood. Okay, it ties you down. So it's made the choice for you. So don't ever be fooled by this argument, that the frequentist method is objective. Nothing in life is objective. Everything is subjective. Okay. All right. So that criticism is just a nonsensical criticism. And usually, frequentists are often very scared of Bayesian analyses. And that's why they come up with these kind of ridiculous arguments. So don't be shaken by any such argument, because none of it ever makes sense. And I will talk more about that later, right? Okay, so then the next thing we are doing is we're going to define a prior for each of our parameters. We're going to first evaluate whether the model makes any sense. We will do this using fake data simulation, right? I don't like this term fake data. We can call it simulated data, right? But it's okay for now. This is the term that Gelman uses, so we'll stick with it for now, right? Gelman is a famous Bayesian statistician. Anyway, so now what we will do is before we even fit the data, we will use fake data simulation to understand whether the model makes sense. And we will also use something called prior predictive checks and posterior predictive checks on the fake data to check, whether our model is sensible or not. All this stuff will be discussed at some point, but I'll give you some hint to what's happening today. Okay. And then we're going to start using software to derive the posterior distributions of each of the parameters. This is the end goal, of the Bayesian analysis. And we're going to, as I showed you yesterday, we will produce the marginal posterior distributions. What the model is underlyingly doing is that it's generating a joint probability density function for all the parameters. If you have 150 parameters, you have a 150 dimensional joint probability distribution. And what we're going to do is we're going to extract the marginal probability density functions of each of the posteriors, each of the parameters, right? So I'll show you today how to do that. Fortunately for us, this step is super simple today. It's just one line in R. You don't have to do any work to figure this out. But lying behind this is really deep computational effort, right? It's a lot of work somebody did for us, such that we can do this so easily today, right? All right, and so then we will check some model convergence, do some diagnostics to check if our model converged. As I will show you, we will usually not have any problems, right? Because we are using these so-called regularizing priors. And then finally, we will summarize the posterior distribution. That's what we publish in the paper, right? I'll show you some examples from real papers. And then once we've plotted the posterior marginal distributions, especially the one that we really care about theoretically, we can make our scientific decisions, right? That means that we can act as if we learned something from the data. Whether we actually learned something from the data is a separate question that would require a full lecture on its own, but we can act as if we learned something from the data. We can make a decision about the data, okay? So that's what we will do, right? And I will, of course, give you examples. So let's do some specific examples now. The first example I'll start with is a simple linear model where I have some reaction time data in milliseconds. This is real data that Bruno created by doing the experiment himself. So this is the data set called DF spacebar, which is available in this library, bcogSci. I know that some of you are unable to install this library. That's not a problem for our discussion. The reason is that if you go to the home page where this library lives, right? So I'm showing you that web page now, hopefully. Yeah. So if you look here, there's a directory called data. And even if you can't install this package as an R package, you can just download the data set that you want to look at, right? So DF spacebar, where is it? Here somewhere, right? Here, right? So this, just download this thing here. Just right click. I suppose this is what should work. Save, will this work? This might work, let's try. Yeah, right? So DF spacebar will be downloaded onto my hard drive if I right click on that thing, and then I can just keep working as if I have that data set by loading it. You know how to load data, so just do that. If you can install this library, that's nice. If you install it, you can just say library bcogSci, load the data with this command, and we are ready to go. So let me just actually switch to R Studio to show you what's going on here. Where's my R Studio now? Never mind. Let me just open this. Right. So let's go to the beginning of these slides here. Yeah. So here we go. So I'm going to just load this library, and I load my data. So if I look at the data, let's take a look. So in this data set, what I have is something very simple. I have reaction times and trial ID, right? It's just two columns. It's just one subject. That's why I don't have a subject column. The subject is Bruno, the other guy who co-wrote the textbook with me. So this is Bruno's data, and he's just pressing a button on the computer, right? They're just recording the button press times. And our goal is, like we discussed a couple of days ago, our goal is to figure out what the average reading time is in these data. Of course, I could do this in a very simple way, right? Remember, I could just do the frequentist thing, and I could say DF space bar, right? And then I could say, give me the summary of the data. So I've got the minimum is 110 milliseconds, maximum is 409, average is 168.6. Memorize this number. Okay, this is the maximum likelihood estimate. This is the value that gives you the highest point in the likelihood function. You remember? That's the sample mean. I want you to also notice that this distribution is highly skewed, right? If you're an experienced modeler, if you just look at this summary statistics, you know that there's a huge skew in this data. How do I know that? The mean is 168. The minimum is 110. The first quartile, so 25% of the data is to the left of 150 milliseconds, right? The third quartile is 181 milliseconds, okay? So 25% of the data is to the right of 181 milliseconds, but the maximum is 400. That tells me that there's a skew. And if I plotted this graphically, I would see the skew. You see this? There's a heavy right skew here. This is by no means a Gaussian distribution. No amount of fantastic thinking, magical thinking will allow this to be a normal distribution. Nevertheless, we will do the standard thing that people do and pretend that it's a normal distribution, right? For now, okay, then we'll fix this problem later. Okay, so I just want to point out, first of all, that this is a very important first step in any data analysis. People are used to just loading the data and running the linear mixed model command. That is a very dangerous thing to do. It's a dangerous and actually an insane thing to do, right? And I want to quickly show you, I just want to teach you a lesson right now that should cure you of this disease forever of, just loading the data and running the analysis. So this is a typical way that I was taught to do data analysis. So I have made these mistakes myself, by the way. This is not, I criticize other people for this, but like I've done exactly the same thing in my life, right? So plenty of data like this. So let me show you, okay? So this is the typical way that we analyze data. And I'll just show you what goes wrong here. So this is that relative clause data that I have from a published study. So there's some reading time and there's some condition or something. And there's, right, one plus condition, vertical bar subject. This would be what one would typically do in this kind of analysis. The two condition study, right? So I would think that, yeah, I can do this and I can get an answer from this kind of analysis, right? Let's see if this works. I'm just doing this blind now without checking. Yeah, whatever, singularity warning, who cares, right? I just want to know if it's a significant effect or not. So I don't care if my variance covariance matrix is significant, is singular or not. They're both singular, by the way. So the random effects are total garbage, but never mind. So I've got a significant effect. I'm ready to publish this paper. And this is exactly what happened with this data set. It was published. But you know what's interesting about it? Let me show you something cool about this data set. If they had spent 50 milliseconds, plotting the box plot on this data by condition, they would see the following. What happened? Sorry, I didn't type this correctly. My plot will not show anyway because I don't have any of this, right? So let me show you something cool here, right? So if I zoom this, you see what's going on here. Take a look. What's happening here? There are two conditions, object gap and subject gap. What do you notice?
So the means are actually, like there's just a giant left tail or right tail in the object gap.
So what we are doing in the linear mixed model is we are checking whether there's a difference in means between these two conditions, right? What's interesting about the mean, it's a property of the mean, is that it's very sensitive to extreme values. Very, very sensitive, right? And so what's going to happen is that these 2 or 3 data points, right, they're pushing up the mean of this condition, leading to a significant effect. Right?
Yeah, but then if you look at the median, they're actually Very,
You
very
look at the
close.
median, which is probably this dark line here. You see that there's basically no difference. So what's very interesting about this data set is that if I just were to remove a couple of these data points, 1 or 2 data points here, the effect would disappear. This is a published analysis in a journal article. Okay, they never bothered to check that. So sorry,
Has there been a correction issued?
I'm sorry?
Has there been a correction issued since then?
So actually, I just made a mistake. I'm really tired right now because I've been teaching for 3 days. Now, third day now, I'm really exhausted. So actually, this is the wrong data set I'm showing you. Let me show you the correct one. The same problem holds in this data, but this is another point that I wanted to make. But let me just show you the correct data set. Just 1 minute. Which one is it? Just 1 second. This is a very important point. I want to get this across. So I don't want to proceed until I've made this point. So just give me a second. This data set has a similar problem, okay? But I will answer the question that you just asked. I will just, yeah, here it is, right? So it's Gibson and Wu. Gibson and Wu. This is the data set I wanted to actually show you. I'm sorry about that. And so if I look at this data set, what does it look like? This is Chinese relative clauses, right? This is about Chinese relative clauses. It's a very controversial point. So the claim in this paper is that object relatives are actually easier to process than subject relatives in Chinese. If that were true, that would be a very surprising fact, because almost every language that we have studied, in the history of psycholinguistics shows the opposite pattern. And so if I show you what's happening in this data, sorry. Oh, gosh. What was this again? It's type, right? Instead of condition, they call it type. Let me show you what's in this data. Right, so, right, so this is the data. So here's the subject relative, here's the object relative. You can see that these extreme values, this is one word. This is reading times on a word. People are spending more than 5 seconds looking at that word. And these data points, these 3 data points are actually causing the difference in the means, right? So if you fit this model, let me just do this, RT type, right? So I'm going to drop the varying slopes for the moment, right? Just drop the varying slopes. And I'm going to fit this model. It's a bit simple. Right? And so if I fit this model, I get a nice significant effect. Where is it? Where is it? Yeah, 2.5 T value. Okay. Super cool significant effect. So if I now log transform this data, let's see what happens. Take a look at the T value now. Do you see the T value? It's 1.6. It went from 2.5 to 1.6. The reason for that is that the log transform is going to compress these extreme values and downweight them. And it's just these 2 or 3 these extreme values that are driving that effect. So to answer the question that was asked, this paper was not retracted. This was the only significant effect reported in that paper. And the result still holds, as a result in the literature. So these kinds of problems arise because, it's not the case that the authors actually, are doing something that they were not taught to do. This is what we are taught to do. When I was taught to do data analysis, I was just taught to load the data and run the model. That's it. Don't check anything, right? So you should never do that. So I just wanted to make sure that you guys first plot your data and take a look at what's happening there before you do anything else, because the price to be paid is very high, right? So we are about to publish a paper or release a paper in the public domain where we analyzed 58 articles data from Journal of Memory and Language. We were asked by the editor to do this. And what's interesting is that only a fraction of those data sets are even reproducible, let alone talk about the significant effects and so on. It's a really dramatic situation that basically the analyses that we publish, right? Nobody knows how those analyses came to be in most cases, right? The published result is unknown. And another interesting thing is that in most of the data sets that I have analyzed from the Journal of Memory and Language, I could not find a significant effect where one was claimed. Most of the papers, that is true, okay? And what is even more dramatic is that in many of these JML papers, JML is our top journal, okay, in the field, even the published claim is not statistically significant, right? So what the numbers that they published in the paper are not significant. So the reason I'm saying I'm ranting about this is that you should not get obsessed about whether the effect is significant or not. That is the wrong question to ask. Your goal should be to get an estimate of the parameter of interest. In this case, it would be the difference between the two conditions, and an estimate of the uncertainty of that parameter. That is the informative thing. Okay, whether it's significant or not is almost an irrelevant question. And I will of course elaborate on this later on. But first step, plot the data. There's obviously some skew. We will deal with that later. So let's go on. Okay. So our goal now is to figure out what an estimate is of the underlying, mean reaction time mu, and we're going to get some uncertainty estimate on that in the end, right? And we also know that there's some noise in the process. That's the sigma parameter. So we're going to get an estimate of that as well, right? We deal with the skew later. All right, so here we go, right? So this is our model, simple model. The way I will write this model in the textbook as well as in these slides is that n, the number n, or the variable n, will always represent the row in the data frame, right? So if I have 547 rows in the data frame, then n ranges from 1 to 547, okay? So n indexes the row in the data frame, and I'm assuming that all the data are coming from this normal distribution, okay? All right. So we go ahead and fit this model. And in order to define the priors on these parameters, right? Let's start with some priors. So we're just starting somewhere, okay? I'm going to give you some starting points and then we'll do something more intelligent. This is not a very intelligent decision, but let's just start with this, right? So we will say, for starters, that the prior on mu is going to be a normal distribution centered on 0 with a standard deviation of 2000. This is a very uninformative prior. Why? Because the prior says that we are 95% sure that the mean reaction time mu is going to range from minus 4,000 milliseconds to plus 4,000 milliseconds. Not very sensible. Why? Because mu cannot be negative. I know that, right? But what I want to show you is that nothing bad is going to happen if you choose such a crazy prior. This is such an uninformative prior, right, that it is going to have almost no impact in determining the posterior given the data. It's a very vague prior, okay? And even though this prior contains ridiculous, impossible values, they will eventually play no role in determining the posterior because the data will never have any negative values, right? We just saw that. This is the distribution of the data. The lower bound is 100. So even though I've defined an observed prior for mu, nothing bad is going to happen. All right. Secondly, what I defined for sigma is something called a truncated prior. So this you might have seen if you've read the chapters 1 and 2, you will have encountered this already. So what I've done here is I've chosen a normal prior with mean 0 and standard deviation 500, but this time I will not allow any negative values. Why? Because sigma can never have negative values. Now you must probably you want to ask me, why didn't you do that for mu? I could have done that for mu, right? But I just wanted to show you that nothing bad will happen if I allow negative values here. Probably nothing bad will happen if I allow negative values here also. But in the models that we will fit, we will strictly limit the distribution for sigma to be positive. Okay, we will always strictly limit it. So, so let's go on. Okay, so this is how I will write it. Sometimes what I will do is I will write this normal with an underscore plus here that indicates, what that indicates is that that sigma can only have positive values. Okay, so that's the convention. All right, so Now visualizing the priors. If I visualize the prior on mu, I see that there's a 95% range that goes from -4,000 to +4,000. These are plausible prior values that are set for mu. This is my decision as the modeler. Here is my truncated prior, right? You will notice that this truncated prior now is not a proper probability density function. You remember? Because I've sliced off half the area under the curve. So I would have to multiply this with 2. This whole PDF, I would have to multiply with 2 to make the area under the curve sum to 1. That's the normalizing constant, okay? So underlyingly in Stan and so on, we will have to do that work. Later on, when you do advanced modeling in the later chapters, which we won't cover in this book, if you ever code your models by hand in Stan, you will have to fix the PDF by putting in the normalizing constant, right? So that will happen later on. But luckily for us in this course, we don't have to care about this. The BRMS function will take care of all this for us, okay? So it's all happening behind the scenes, but now you know what that means. All right, so what we're gonna do is that once we've defined this model, we've defined our model now fully. We've got the priors and we've got the model specification here, right? So in Bayesian modeling, when I say model, the model includes the priors. A model consists of this specification or this specification plus the prior specifications. So when I publish my model in a paper, I will always specify what the underlying likelihood function is, this one here, and what my priors are. These two pieces of information must be provided, right? That constitutes the model. Right, so what I'm going to do now is once I have specified the model, I can actually generate data from this model now. Without having observed any data, I can produce data from this model now. Why? Because I have a prior distribution on the parameters, and I can use those prior distributions to actually just run them through this model here, or this model here, and just produce this simulated data. And this kind of simulated data, before we've seen any real data, is called prior predictive data. The purpose of producing prior predictive data is to check whether your model will produce sensible data at all. If your model starts producing negative reading times, you already know something's wrong with your specification. Right? So that's the purpose of this prior predictive check. And so that's what we're going to do. And formally, we write the prior predictive data like this, right? So we're going to produce n data points from this model by taking the priors on the theta parameters. And what we say here, formally, what I'm doing here is I'm averaging over all the data that the priors would, all the parameter values that the prior would produce. So formally, what we say is that we are integrating out the parameters. We are averaging out the parameters and producing data, right? And so this is called integrating out the parameters to produce prior predictive data. And the way to do it in R is that you take a sample from each of the priors, right? I specify these priors. I repeatedly take a sample from each of these priors, generate some data, then take another sample from the priors, generate some data, so a vector of n data points. If I do that 4,000 times, I've got 4,000 sets of data sets that I've produced. Okay? So that's how I produce prior predictive data. Very easy, right? Okay, so we would get basically a matrix, right? Of if I do 4,000 simulations like this, I sample 4,000 times from the prior and produce, let's say 400 data points each time, I'll get a 4,000 by 400 matrix, right? That's my prior predictive density, right? And so then I can actually plot it, right? So I'm doing all this now. All this code you can look at, sorry, this fell off the screen because it's too small. So let me just pull it up. Let me just do this. I will fix this afterwards. Oh, what am I doing now? Prior predictive. Oh, this is the wrong file, sorry. There is. Right, so here we go. Let me make this bigger, get rid of all this. Here, right? So I've taken this extra dist library. The reason I have this is so that I can sample from a truncated normal. So I'm going to do 1,000 simulations, produce 100 data sets each time. And so what I've done here is I've created a 1,000 by 100 matrix with how many columns? 100 columns. Okay, so there'll be 1,000 rows and 100 columns, right? That's my Y matrix here. And then what I'm going to do is I'm going to generate 1,000 samples for the mu from this prior distribution. I'm going to take 1,000 samples from the truncated normal for the sigma. So I've got 1,000 samples from the prior distribution for mu, 1,000 samples for sigma, and then I'm going to do the following 1,000 times. Each time, each of those 1,000 times, I'm going to take one of the 1,000 samples of mu and sigma, generate 100 data points, and save it in the ith column, in the first column, second column, third column, then the 100th column. So what I will end up with when I run this command is a Y matrix that contains 1,000 rows and 100 columns. And each of the columns is a simulated data set that I produced from the model without seeing any data. It's that easy, okay? So let me just do this quickly. This will run real fast. This is all really, really fast, right? So once I run this, you see it's instantly computed. It doesn't take any time. And if I look at Y, what I see is I've got 100 columns, and I'm just showing you the top part of this distribution, but each of these columns is simulated data. Look at this. There's some ridiculous data that this model is producing. You see that? That's because of my observed prior on the mu. So I know that this is a nonsensical model already, okay? Never mind. It's a good exercise, but let's just do this, okay? So, okay, so this I will fix later. I'm sorry about that. And so what I'm doing now is I've generated some fake data. Some of the columns, I've just chosen 4 random columns to show you what this model is producing. And I mean, this is just one random data set. And you can see that most of the values are negative here, okay? This is not good news. The prior predictive check shows that this model is no good, right? So I'll have to fix that later on. I will do it later, right? Okay. So what we could do is we could try to redefine the prior on mu to have only positive values, and then we can try again. But what will happen, you know, if you try this, and you should try this. Of course, it's all the source code is in these slides. You can take a look later. What will happen is that you will still get some negative values. And the reason is, even if the prior on mu only allows positive values, sometimes this mu value will be small, right? It will be, let's say, 1 millisecond or something. That's still positive. But the standard deviation is still very large. That means it will allow, because this is the normal likelihood, it will still allow negative values. So you would still produce negative values, right? So that's not going to be enough. We'll have to do something more. And I will show you what we will do, right? So this is all the code for generating this data again. See what I've done here? I've taken a truncated normal for mu. So I'm only allowing positive values for mu, but I will still get negative values. Still get negative values. So in this case, these two, I'm lucky. I got lucky, right? I managed to get some large values of mu. So I see more sensible data already. But if I were to look at all the data, I would find some negative values. Okay, so that can happen. All right, so that's how the story works. But now what I'm going to show you is how I would actually do this kind of prior predictive check. You know, the prior predictive check that we just did was done by hand, so to speak, in R using the for loop. But you can also do this using Stan, which is the programming language we are using underlyingly in the rest of this course. Okay? So I'm going to now give you a quick introduction to Stan. This is your first contact with the modeling framework. And I'm going to show you how to produce prior predictive data. Okay, so here we go. What I'm showing you here on the screen is a Stan specification for a model. The model is called prior pred. I just called it prior pred. You could have called it anything. You could call it M1, for example. And this model specification is going to define in Stan syntax the model that I defined earlier for you guys, So the beauty of Stan is the important, insight that you should gain from Stan is that the Stan programming language allows you to literally write out the mathematical form of the model, in Stan syntax. So normal plus, so truncated at 0, 500, and my likelihood is going to be y is a normal, right, with mu and sigma. This is a full specification of the model, and we will literally write it out in Stan. Literally. Okay, so how do I do this? If you look here, in the model specification, there's a block in the Stan code called the model block, and a block is always contained inside these curly braces. Okay? So this is the heart of the model, and the model is simply defining the priors on mu and sigma. You see that? I've literally written out the mathematical model. Okay, so that's my prior. Those are my priors. So there's two other blocks that come before the model block. The first block is the data block, which contains information about how many data points I have. So what I've written here is that the number of data points is capital N, and the N is of type integer. Now, because Stan translates this model code that I'm writing here, Stan will translate this into C syntax, and then it will compile it on your computer. So because C requires type specifications for every variable like capital N, that's why we provide this type specification. And this semicolon is something that you don't use in R normally. You could use it in R, but we don't have a line ending with a semicolon in R, but in C we need that line ending. So that's why they put this line ending in Stan syntax. Okay, so this semicolon indicates the end of a line. Okay. So this is the syntax for the data block. And what you notice here is that I've specified the number of data points. This will be 100, for example, right? And in the next block, which is the parameters block, I will specify the two parameters of the model. And notice that what I state here is that the two parameters have type real. That means they're real numbers. That means they're continuous values that can go from -infinity to +infinity. Right? But I have constrained the real number line by saying that the lower bound of the real numbers is 0. Okay, so in Stan, I can actually limit the range of possible values of mu. So that's what I've done here and here. Okay. All right, so then I specify my model, which is mu and sigma here. Notice that I've not specified any likelihood here. Why? Because I'm only using this code to generate prior predictive data. And so in Stan, what you do is, if you want to generate simulated data, there's a block called generated quantities. Notice that there's a space between generated and quantities. There's two words, okay? So in this block, I will put in a for loop that will produce n data points. What is capital N? It's the number of data points that I decide to produce. I could choose that number of data points. And I've created a vector containing n empty cells. This is called ysim. And in this for loop, I'm using the random number generator available in Stan to use this normal likelihood. I'm plugging in the mu and sigma values and producing simulated data. This is exactly what I did by hand in R a few minutes ago. Okay, so you can do that in R or you can do that in Stan. So it's exactly the same thing. And what you will get at the end of all this is some simulated data, which is exactly like the Y matrix I showed you earlier. So what's the syntax? So let me walk you through the analysis of the way to use this. First, I load my library rstan. So this is the Stan library that's used in R. If any of you uses Python, there's a package called PyStan that does all the coding in Python. So you could use it there. So, but we are only going to use rstan here. Okay. So what I've done here is I've loaded the library. Now, because my laptop has got, I think it's got 8 cores or something like that. So I'm asking R to detect the cores on my machine and use them for parallel computations to speed up the computation. Okay. And then I'm loading this Brms library because I will need it very soon. Okay, so Brms is a library that uses this kind of stand syntax underlyingly, but it provides some easy syntactic sugar that makes the model look like the Elmer function, right? So it makes it easier to write the code, because when beginners are working with stand, they might be, reluctant to write pure stand code. So just as an entry point, we will allow you to, write the code just like Elmer models. But when you become an advanced modeler, when you start building customized models, then you will want to switch to stand code. That's why I wanted to introduce this to you. So I just want to point out briefly that the reason I favor writing models in stand, there are two reasons. The first reason is that you can customize your model to do whatever you like. Okay, that's not a capability that's available to you in Elmer or BRMS. And the second advantage is that you will understand for the first time in your life how a model is actually assembled, right? So I understood linear mixed models for the very first time after I started writing stand syntax. I didn't really have any idea what I was doing with Elmer, right? So until I actually wrote the model down mathematically in stand, or actually it was JAGS that I started with, which is another programming language, but it's the same point. Writing code like this will really help you deeply understand what you are saying about the generative process. This is a huge insight. Once you realize what's going on, this will just blow your mind. Okay, so that's why this is so important. So anyway, let me go on. So what I've done is, notice that I'm setting up my data to contain only one piece of information. How many data points will I generate? That's it, right? That's because in this stand syntax, this is the only information I give in the data block. Later on, when we actually fit data, we'll give more information in the data block, okay? And so one property of stand is that it expects the data not in a data frame format, but in a list format. So that's why I have a list object here. And so now we get to the critical, command that produces the prior predictive data. I use the stand command in the rstand package. And what this says is that I should use this prior pred model that I just defined, this model here. I saved it as a character string. That's what this double quotes is for. So I've written out all this code and I've saved it as a character string. So prior pred contains a character string, and that's going to go into this model code thing here. And then I'm specifying my data. My data is just this list object here. I'm telling stand to fit 4 chains. I will explain this in a minute. Just ignore this. And there's some warm up and iterations that I've set up. I will explain all this later, right? So these are just specifications in stand. But the important thing is the model and the data here. The data is just the number of data points I want to generate. And I save the results of this computation in M1 prior pred, right? So if I do that, I fit the model, and then I'm going to extract the simulated prior predictive data from this object that I just fit using the extract function. And once I look at the object, what does it contain? What it contains is 4,000 rows and 100 columns. You see that? So this YSIM matrix contains 4,000 simulations. What I've done is 4,000 times I've generated data sets of length 100. So if I look at any of the columns, I will be looking at one of the generated data sets. Okay. And so I can, for example, this is the 100th simulated this is the 100th simulation. I'm just showing you a prior predictive distribution, and just happens to look pretty reasonable. But as you will notice, the prior predictive distribution shows very slow reading times. Remember that our reading times are more like 400 milliseconds was the maximum, right? This is in the thousands of milliseconds. So the prior predictive data is not super inspiring. Like, I would not get overexcited about my priors. So I can do better, and we will do better later on, right? But it's okay. I mean, it's a good start, right? So this is how you check whether your model makes sense, right? So now what we're going to do is, so I still haven't looked at the real data yet. The next step that I will take is that I'm going to generate fake data with known parameter values. I'm going to choose point values for the mu and sigma, generate some fake data, and then I'm going to check if my model can recover those parameter values. Okay, so this time I'm actually using data, but I'm using fake data. So how do I do that? So first of all, I'm going to have to define, change my model. So this model is now called M1. This is still standard syntax, okay? So I'm going to define a model which doesn't just contain the number of data points, but it also creates a data vector now. This will be the simulated data that I will put in, and it will be of length n, okay? Everything else is the same. The parameters block is the same, right? The generated quantities block is the same, but there is one new development now. Now, because I have real data, I'm not only putting the priors in the model block, but I've also put in the likelihood function. You see that? This is a full model specification for this model. This is literally, this model block is literally writing out this detail here. Right? And so you can imagine what's going to happen later when we have a linear mixed model. This part will be highly elaborated. Will be very heavily elaborated. And so there'll be many more parameters in this model, and there will be priors on each one of those. And we will just write that out. We will literally write that out in the model block. Okay. So that's the beauty of this whole framework. And so now that I have actual data, I'm ready to go. What I do is I'm going to first generate this fake data. So what I do is I will generate 500 data points with a true mu of 400, a true sigma of 125. Notice that these are point values now. Okay, so I actually have a gold standard now. I'm playing God basically, because now I'm pretending that I actually know the mu and sigma. This is never true in real life. But in this world, in this simulated world, I do know the true values, right? So what I do is taking these true values, I generate some simulated data using R norm with 500 data points. This is my fake data now, this Y, okay? So then I'm gonna take this fake data, make it into a list object for for stan, sorry. So this is my Y vector, this is my length of data points, 500, and this is my data object, which I will feed into stan now, okay? So in stan, I'm gonna give it the model M1, which I just defined, this model M1, okay? And then I'm going to give it the new data object, which contains two pieces of information. This we can ignore right now. And then I'm going to extract from this fitted model. Here's the fitted model. I extract the mu and sigma, right? This is the big moment for us, because what we are doing is we're extracting the posterior distributions of mu and sigma. We're going to plot this distribution and compare it with our gold standard values, which are 400 and 125, right? So when I extract these posteriors, I can use the histogram to look at the posterior distribution for mu, the posterior for sigma, right? And what I've done is I've plotted this vertical line. I don't know if you can see it. There's a vertical line here that represents the true mu, a vertical line here that represents the true sigma, right? And what you notice is that the posterior distribution is nicely centered around the true values. So this is telling me that the model is able to recover the true values of these parameters. If I were to actually know what the true values were, the model would discover these true values. Okay? Right. So what I have done now is I've shown you two ways to evaluate your model. The first way was to use prior predictive checks to see if the model even produces sensible data, given the priors. The second is to use gold standard values for the parameters, run it through the model to see if the model can discover the true values of the parameter or not. Once these two things are done, you know that your model is a sensible one. So what's happened in this particular case is, even though the priors are nonsensical, and we saw that in the prior predictive checks, the model will still recover the true parameters, right? That's because the priors are so vague. The likelihood is dominating in determining the posterior. And that's why we'll still get sensible measures, right? So this is this should make you feel a little bit less nervous about priors. Because the lesson to learn here is that if your priors are relatively vague, then your maximum likelihood estimate is going to dominate, or your likelihood will dominate in determining the posterior. Right? So the worry about bias can be assuaged, by having uninformative priors. And as I mentioned earlier, normally when we do an analysis, we will do a sensitivity analysis to see how the posterior changes as a function of increasingly specific, increasingly informative prior specifications. We will get to that, of course. So now, once we have fit the model on real data, we can actually do one more interesting thing. The interesting thing that we can do is that we can actually produce future data, something called posterior predictive data, having derived the posterior distributions for the parameters, right? So what's happened is that we have got these posteriors for these mu's. These are also probability density functions. So we can now use these probability density functions to produce future data now. These parameters, these posteriors now are informed by the data that we used. So they're actually, we have learned something from the data, and we're going to use that knowledge to produce future data now. And that future data is called posterior predictive data. So the way we write it formally is that we will produce predicted data given the observed data. And notice that there is no theta parameters here anymore. The reason is that we have integrated out the theta parameters. We average over the the posterior distributions of the parameters, and we can produce the future data. So that's how we do this. And again, this amounts to integrating out these unknown parameters. Right? I discussed this in chapter 1. If you're not familiar with this idea, you can look at the chapter 1 discussion and try to make it easy to understand. But the important thing for us is that intuitively, it's very easy to understand what's happening. We have these posteriors. We're going to use these posteriors to produce new data, just like we did with the prior predictive data, right? Except that we have been informed by the observed data now. Okay, so posterior predictive checks. So how would we do this?
Can I ask?
Yes.
Sorry, can I ask one quick question? The second one, the fake data simulation, when you say the likelihood dominated, so it was like my question was like, do we set the fake data, the number of fake data to the planned number of samples when we do this?
Yeah, that's a very good question. So when we are generating simulated data, we have to decide on the sample size. That is an important question, right? So you could, what you could do is that there are two ways, right? So one way is that you already have data. Let's say you're getting ready to analyze existing data. That's one situation that we are often in. And in this course, we will always be in the situation that we already have existing data. We are setting up a model for that. In that case, you should use a number of data points in your observed data as the data for generating simulated data, right? The other situation is when you're planning, literally planning a future experiment. You're setting up the stage for an analysis. You do not have any data on you. At that point, you have to decide what sample size you're going to use, right? That's a decision you have to make. And there you have a lot of freedom, right? So what I typically do is that because I have a lot of time and money available to me, right? I am a senior researcher with a very large lab. I have a large budget, and I can wait even 4 years, to collect data. I have done this. I've waited up to 4 years to collect data, right? But students don't have this luxury, right? Students are working under a timeline. So you have to decide what your practical sample size is going to be for your particular problem and then work with that, right? As a student, you have no obligation to, try to get as much data as possible. You can't do it because you don't have the resources. So that's okay. So you're learning to do research right now. That's the purpose of being a student. Yeah.
So maybe, for example, in this case, like we did like 400, but it may be the case that we do like 100 for our case.
Absolutely. Yeah. So so right now we are looking at a toy example, just button pressing, right? Later on, we'll look at repeated measures data. And there what will happen is, suppose I have a 2x2 factorial design. I have 4 conditions. I'm going to have to decide how many items will be shown to each subject and how many subjects I will have, right? So there's a physical limit on this. Like each subject, you don't want to expose each subject to more than maybe 120 sentences. That automatically constrains the number of items that you can have, because you're going to have fillers as well, right? And then you have to decide how many subjects you will run. So typically, for psycholinguistic reading studies and so on, I generally prefer to have, in my own lab, I would prefer to have something like 400 subjects for running a self-paced reading study or something. But if my students are doing an experiment, I would be happy if they just ran 100 subjects or even 80 subjects or something like that. When we are running ERP studies, when we are recording electrical signals on the scalp, we are often heavily constrained by time because we have a project running for 3 years. So we will collect maybe 80 subjects data, which is not enough actually. But that's what we will do. It will take us a long time to do that because each subject takes about 2-3 hours. So, and in the Corona times, it's even slower. So 80 would be reasonable for that, for a student or a postdoc or something. So yeah, that's fine. You can decide how to, choose a relevant sample size for your particular problem. This is a subjective issue that you have to address, And I actually have a paper on this that you can look at. It's on my homepage. And so this is just a paper I recently wrote. Where is it? Here. So I describe in this paper, it's under review right now. It's not published yet. It's called sample size determination. Sample size determination for Bayesian hierarchical models commonly used in psycholinguistics. So I describe a method that's actually due to some statisticians. So there's 2 statisticians who wrote this paper. So I apply this method to show how to compute sample size in advance, before running any experiments. So there's a method for doing that. So you can look at this paper later on if you want to, right? This uses Bayes factors. And I've provided all the code and data so you can reproduce this analysis. By the end of today, you will know how to run this kind of model, right? So you're almost there now. Okay?
Great, thank you.
All right.
Yeah, thank you.
So, all right. So now I'm going to show you how to fit this. Yes, please, go ahead.
Yeah, sorry, I wanted to ask you a question as well. Previously, you said that the model was okay because the data was centered on the model, but I actually didn't get how you did say that. I mean, how you decided that the model was okay.
How did I decide that the model is okay? I decided that by fake data simulation and checking if the model can recover the parameters or not. So one possible thing that could have happened that would be very bad is if the true sigma was something, let's say 250 or something, okay? And the model posterior was showing a range between 110 and 130 milliseconds. That would be a very bad situation. Are you with me?
Yeah, okay.
Yeah. So that would be a sign that the model is not recovering the parameter. So here the mean is 400 or so, right? And if the model if the true mean had been, let's say 600, and the model was telling me that the true mean, that the posterior is centered around 400, that is bad news. That is very bad news. Yeah, that means that the model is misspecified.
Okay, thank you, I got it.
And if you read the rest of the book, we will show you situations where the model is unable to recover the parameters. There are situations like that. And then you have to figure out what to do, okay? You have to find solutions to that problem.
Yeah, okay, thank you.
So I'll discuss later on. But that's an advanced topic. Okay, so now let's look at this. So now what I'm going to show you is how to fit the same model that I just specified in STAN, how to fit it in BRMS. The advantage of BRMS is that it uses the familiar LM and LNER syntax. So the syntax for BRMS is the following. First, we have to define some priors, and this will be saved as a vector, each of which specifies a prior. So for the intercept, that is for mu, I will define a prior in this way using the set prior function in BRMS. This is a BRMS command, which says that the prior is a normal 0 to 1000. This is the standard deviation, right? And the parameter that I'm defining the prior for is defined here. So in the linear model, the mu is the intercept, if you remember, right? Therefore, I'm going to call it the intercept here. This is a reserved word in BRMS. You have to use this word to define the intercept. And the prior for sigma for the standard deviation is defined here. Okay, so that's the setup. And then the syntax in BRMS is very simple. It's just like with LM. We use this command BRM, dependent variable, tilde, intercept, name of the data set. This is the actual data set now. The prior specifications are given here. And I'm defining some details here, which I won't discuss yet. I'll discuss them later. I'm defining the likelihood here. So in BRMS, the normal likelihood is called the Gaussian because that's just a synonym for the normal. And so the family that I'm using, the likelihood family I'm using is the Gaussian here, normal distribution. This is some control parameter that I will discuss later. Once I fit this model, I can then extract the posterior distributions and again look at the mu, which is now called the intercept, and the sigma. And you notice that this posterior and this sigma is now very different from my prior my fake data simulation based mu and sigma, right? And the reason for that is what? The reason is that this is actually based on the data that I have got from the button pressing data set. This is actual data that has informed the posterior distribution. So the average is around 168. Do you guys remember what the mean of the data set was? It was 168.8 or something like that, right? So this model is actually influenced by the maximum likelihood estimate because of the vague priors. And it's giving me a posterior that is centered around the maximum likelihood estimate. Similarly, the standard deviation is also basically the maximum likelihood estimate. So I'm getting something like 25. Okay, so these are the posteriors. This is what we get from the model, right? And we can now draw our inferences from this these posteriors. So if I was publishing this result, what I would do is I would actually plot these posteriors in the paper. Okay, so I would just show these posteriors, and in the text I would write that the mean was such and such, and the 95% credible interval was such and such, right? That would be the summary of the model output for me. Okay, so what's interesting now is that we are now ready to do anything that we possibly want, because all that will change now is that instead of writing this simple model here, I will have some predictors here. I can add linear mixed model syntax here. Everything will remain the same. All that will change is the prior specifications. We'll have to keep adding priors for the new parameters. And this code will just repeat again and again now. Okay. The only other thing that will change is that we will change the family of functions that we will use. We will use a more reasonable likelihood function, not the Gaussian for reading times. Okay, so that's all that will change now. And so, okay. So I'm going to now explain all the other commands that I was skipping right now. So let me just, I'll just talk about this in a moment. So let me just get some water. Just wait a second. So, what's happening underlyingly with the STAN model is, so if you remember, when we started this course, the way we generate, simulated data for a parameter, the way we would generate it is if I want to generate data from, a normal distribution with mean, what was it, 2000 or something, I use the R norm function, right? I can use the R norm function and I can say generate 1000 data points with mean 0 and standard deviation 2000 or something like that, right? So this R norm function, when it produces, simulated data, what it's actually doing is that it's sampling from a particular distribution. We are sampling from a distribution here. Now, what BRMS and STAN is doing is that for your two parameters, mu and sigma, it's also producing samples from the posterior distribution, f of mu given the data, f of sigma given the data, right? This is what STAN, this is the hard work that STAN is doing in the background, right? It's doing the same kind of sampling that we are describing in with the R norm, right? So this sampling that STAN is doing is using something similar to the Gibbs sampler that I explained to you yesterday. The sampler that STAN uses is called Hamiltonian Monte Carlo. It's a fast sampling procedure that produces samples from the posterior. How this is done is beyond the scope of this lecture and this course, but I think the idea is intuitively clear that we are producing samples, from these two distributions. So the way it works in STAN is that that STAN will do the following. Step by step, it will get samples from the posterior distribution. So this is step 1, step 2, step 3, just like in the Gibbs sampler that I showed you yesterday, right? So these are the iterations. We'll call these iterations. And what STAN is doing is that, so on the y-axis, let's say I'm sampling for mu, there are different possible values, right, on the y-axis for mu, right? So initially, STAN will start with some random value, just like in the Gibbs sampler. It starts with some random value in the 0th iteration, right? And then it will take a sample for mu. It will take a sample, let's say this value on the y-axis. It will take this value as a sample. Then in the next iteration, it could take another sample, right? So that's this value on the y-axis. The third iteration, it could take this sample, right? It would be this value. And so as the iterations go on and on, what will happen is that the sampler will be taking a walk. It's taking a walk like this through the distribution for mu. And because the posterior distribution for mu, that is f of mu given the data, it has some shape, right? So what will happen is that the sampler will be getting most of the samples from this high density region. This is the high density region, right? It will be getting most of the samples from here and occasionally from the rear edges of it. So at the end of all these iterations, what will happen is that we will have a bunch of samples. We'll have a bunch of samples from mu, right? And those are the samples that I'm plotting as histograms for you guys, this thing here. These histograms that I'm plotting, these are the results of that sampling that STAN is doing for you, right? So the interesting thing is when the sampler, right, when the sampler is doing its sampling like this over many, many iterations, what we do typically is we ask STAN to run 4 separate instances of those samples, right? So they will be, we call those chains, right? So this is another chain. Let me see if I can get a third color, right? Here is another chain, right? The third chain, and then there will be a 4th chain. Let me see if I can find yet another color, right? Here's another color, right? So I've run 4 chains that will get 4 sets of samples for me, for mu, okay? For mu, they'll get me 4 sets of samples. So we call these 4 instances chains, right? And what's interesting is that if these 4 chains all give you the same distribution, then we say that the chains are mixing nicely, right? And what they say in Bayesian statistics is that the chains look like fat, hairy caterpillars, right? So if you see a distinctive, overlapping of the chains, what that tells you is that the chains are mixing nicely. The mixing is happening, right? And that tells you that that we are getting a robust estimate of the posterior, right? So the bad situation that can happen sometimes is the following, right? So what can happen is that one chain goes off like this, the second chain goes off like this, right? The third chain could go off like this, right? And the fourth chain could go off here. Like this is an example of chains not mixing, right? This is a very bad situation, and Stan and BRMS will both warn you that the chains are not mixing properly. Okay, so these are the two situations that we have to be. This is a situation we have to diagnose. So one way to diagnose this mixing of the chains is to plot the chains to see if they are mixing properly. So what you're seeing here in this plot is for the intercept on the slope, you're seeing the chains, and you're seeing that these 4 chains are mixing nicely. You see this fat hairy caterpillar here, fat hairy caterpillar here. So everything is good. Just visually, I can tell that these 4 chains are mixing nicely, right? And the specification in both Stan and in BRMS is the 4 chains that I set up is over here, okay? So that's this chains command. It tells you how many chains you're going to use. And remember at the beginning when I loaded up Stan, I asked the R system to check how many cores I've got. Remember that? The detect cores command, right? So what I was telling Stan to do is to run these 4 chains in parallel. So all the chains will run on a separate core on my machine. So when we fit more complex models, we run our models not on the laptop, but we run them on an 80-core machine, right? So one of my students does this for me because I don't know how to do it. He knows how to do it. So basically what we use is 80 cores to run the models very, very fast on those 80 separate cores, right? Everything is done in parallel. Then we assemble the chains later on, and we've got everything done in seconds or minutes instead of hours, okay? So that's how you speed up the computation. Okay, so that's chains.
Sorry.
Yes, go ahead.
And if they don't mix nicely, so what should we do?
Yes. So if you get a bad situation like this one that I just described, that the chains are not mixing, right? What that tells you is that there is a misspecification in the model. There is some problem in the way that you have defined the model. And so the most typical solution for this kind of thing is that the reason that you don't get chain mixing is that the sampler is not able to get posterior distributions for the parameter that you have specified, right? The way to fix that is to reparameterize the model. So you change the way that the parameter is specified. So this procedure is called, more generally, it's called reparameterization. I don't know how to spell reparameterization. I think it's spelled like this. I hope it's correct, right? So it's called reparameterization. And later on in the textbook, we show you in detail how to do something called the non-centered reparameterization. This sounds really fancy, but you guys actually already know how to do this. You have already seen this. You just don't know it, okay? So you remember the t-test? The t-test, what is the t-test? The t-test takes your sample mean, right? And the hypothesized mean divided by the standard error, right? This is actually a centered parameterization. Sorry, centered parameterization of the parameters that you're looking for, sorry, right? So let me show you how to convert this to a non-centered parameterization, right? So I would basically take I would say t times standard error plus mu 0 gives me an estimate of x bar, right? This, this is called a non-centered parameterization. So this parameter has been reparameterized in terms of t, standard error, and mu sub 0, right? So this is the general idea. So what we do is whenever we run into trouble with the parameter, in the model, we will create something called a non-centered parameterization. So this will come later on. It's a non-centered parameterization. So this problem we will never face in the models that we are going to fit in this course, right? Because we are never going to run into those complicated models yet. That's an advanced topic that Bruno teaches in the advanced course, but it's all in the textbook. You can read about it there. Okay.
Thank you.
Yeah. So this problem is going to be not a serious one for us. Any other questions? Can I go on? All right, so I have now explained what the chains command here is. The next thing I want to explain is what this iterations is and what the warm-up is. So as I mentioned, what happens in the sampling procedure is that the sampler is for a bunch of iterations. So let's say you decide to run, what do I have here? 2000 iterations. Okay, so there'll be 2000 iterations, right? Sorry, 20,000? No, 2000, right? Sorry. Okay, so I have decided that I will run 2000 iterations, and that's this command here, 2000 here, right? But this warm up is saying that the first 1000 iterations, right, should be treated as an initial walk in the parameter space that will be later on ignored. That means the only samples that I will look at are the samples that come in the last 1000 iterations. That's what this warm-up is saying. This is the warm-up phase, right? This is the warm-up phase. And what this phase does, this initial 1000 iterations, so if I go from 1 to 1000, I basically allow the sampler, so if I'm sampling from the posterior mu, I allow the sampler to look around anywhere in the probability space, in the space for the posterior distribution, and I basically want to wait for a few steps, that is the first 1000 steps, such that the sampler actually starts sampling from the correct posterior, right? In the initial steps, the sampler might not sample from the correct posterior because it's exploring the entire space of possibilities, right? So we discard these first cases, which are called the warm-up, and we only take the samples from the second half. So that's what this warm-up phase does. Now, in the old days, before Stan came up, there was this other software called WinBugs, and JAGS came after this, right? In these pieces of software, what we call warm-up, the name for warm-up there is, what is the word? Burn in, right? I've already forgotten what that term is, right? So they call it the burn in, right? So in Stan, they call it warm-up. It's just a synonym, okay? So you will see this term often, that we had a burn-in of 1000 steps and the number of iterations was 2000. What that means is that we are only going to look at the last 1000 iterations. So notice what's happening here though. I have a warm-up of 1000. Number of iterations is 2000 in each chain. So how many samples am I going to get in the end after I discard the warm-up?
So then 1,000 iterations per chain?
Exactly. I will have 1000 iterations per chain, and therefore I will have 4000 samples at the end, right? If I change the warm-up to 500, right? Then I would have 1500 samples from each chain. So 1500 times 4 is 6000 samples, right? So you will get different numbers of samples depending on your warm-up and your iterations. So this parameter generally we don't need to change, right? But I put it in explicitly because later on the 5th day, so on Friday, I will talk about Bayes factors for model comparison. And there we will have to increase the number of iterations to 10,000 and so on. And warm up will increase to 2,000. We'll need many more iterations. So we will change this, okay? Okay, so now I've explained iteration, warm up, and chains. Family I've already explained. This control parameter is basically used to control the way in which the sampler steps through the probability space. So, imagine again the situation. I've got these number of iterations. So let's say the first 1,000 iterations are done. And now the sampler is going to be walking through the probability space to get samples from the posterior distribution of mu, right? So the steps that the sampler is taking can be controlled by these control parameters. And this is just one of the parameters in the Hamiltonian Monte Carlo algorithm that controls the way that the sampling is done. So I've just set it at 0.99 just from experience, right? So these details I can't discuss right now because it will take us too far into the Hamiltonian Monte Carlo stuff. But you can look at this in the lecture notes. There's a chapter on where we discuss this in a little bit of detail, but not too much. But if you want to know more about all this adapt delta stuff, I recommend that you read the chapter in this book. This very nice book by Ben Lambert. Right, so this textbook is quite cheap and I think it's worth reading. The best chapter in this book is on Hamiltonian Monte Carlo. There's a great chapter in this book. So you guys should read that chapter to get a good understanding of how HMC works, okay? So that's I recommend this book for this purpose. And that's why we don't discuss it too much in this course because Ben Lambert already did a great job in explaining this. All right, so there we go. We've got the posterior distributions. So we are, and I've explained what the trace plots are. These are called trace plots. And they have this distinctive shape when they are done. There's another way to plot this. This is the Bayes plot function, which shows the posterior as a density plot and the trace plot side by side. Typically, I don't use this for published papers because my readers don't need to see the trace plot. They just need to see the posterior, right? So typically, I will only display the posterior distribution. But when I provide online materials, which is always the case, right? When I provide online source code and data, I will show this kind of trace plot in the online supplementary material, okay? So the reader can see that, yeah.
Quickly, so in the trace plot, the iterations are only, they exclude the warm-up, right?
Very good, yeah. Notice that I have only 1,000 here. So the warm-up has been excluded. If I had included the warm-ups, you would notice that in the beginning, the sampler is struggling to sample from the proper space. It'll be all over the place. And then it starts to, converge. I think that in the textbook, we have some examples showing the warm-up phase as well. You will see that the sampler is struggling in the beginning. It's not in the correct space. And it's only after the first 1,000 iterations that it starts, coming to the correct place. Okay, Pratik?
Yeah, good. So basically, we do not plot the iterations, right? Because it might go like haywire. So 4 of the chains might not be one on top of each other.
You don't plot the iterations in the warm-up phase. That's correct, because they will not be on top of each other, or they need not be. And you will only plot the iterations after the warm-up is over. Yes, and that's what this trace plot does by default. Right, it knows to ignore those iterations.
Yeah. And actually, I have a question another on the BRMS code.
Yeah. Oh, sorry. Yeah. Go ahead.
So there was the family Gaussian.
Yes.
Was determined. So
yeah.
In the Stan, compared to the Stan code, where we could also specify like different. So the equations was also for prior and. Actually, we could specify, right, for likelihood as well as for the priors. Here we only have one family. So I'm struggling to understand, like, is it a limitation of BRMS that we can only specify one distribution?
No, no, no. In BRMS, we will change this family in a few minutes. We're going to change it.
Okay. So
Yeah,
because this is only for the prior, right? I mean, if we also have two different, let's say, even likelihood as well, then can we have family 1 and family 2? Or
hang on 1 minute. Hang on. I think there's a misunderstanding here. Let me clarify this. What is this family referring to? Pratik, is this referencing the priors or is this referencing the likelihood?
I think likelihood, is it?
It has this statement has nothing to do with the priors. This is only a specification of the likelihood.
Okay.
The priors are specified where? Here. See that?
Mm-hmm.
So this object is specified here, and this object controls the type of the prior. This is a completely separate specification. And in Stan,
okay.
it's exactly the same. Let's go back to the Stan code. Look at the Stan code. Here, look here. Sorry. Right? So if you look at the model block, here is the specification for Mu's prior, the specification for normal, for sigma, right? And here is the likelihood.
Okay, I see. The confusion came because in BRMS, we did it separately in two different codes.
Well, BRMS tries to be very explicit about what the likelihood is and what the priors are, right? It's I would say that the BRMS code should not be confusing, because this is, remember that I always specify the prior in this object, then I stick it in here into the prior specification, and my likelihood is specified here. It's exactly the same.
Okay.
Yeah. Right.
Thank you.
And later on, we will change this likelihood. This is about to happen. Any other questions? Everything's clear so far, right?
So far, yeah.
Okay. So, so this is on fake data. You could fit this model on fake data. You could fit it on real data. Now this model will work. Okay. So we are pretty confident about this model now. All right. So one question that usually comes is how to summarize the posterior. The way you would summarize it is that you just extract the mean and the 95% credible interval. And you can also ask questions like, what is the probability that the underlying value of the mu is over, for example, 170 milliseconds? Those kind of questions you can ask, right? And so the way you would do that is that you fit the model to the spacebar. This is just repeating the code. Extract the intercept. Okay, I'm extracting the intercept here. I can calculate the mean, and I can figure out the proportion of times that the posterior is larger than 170. So 14% of the posterior values are larger than 170 milliseconds. This could be useful if you have some theoretical prediction, about what you expect to happen. Okay, and the 95% credible interval can be computed very easily by just printing out the posterior interval. So this gives you the 95% interval. So this is the equal-tailed interval, that we discussed yesterday. 5% of the area to the left of it and 5 to the right of this number, right, gives you the range here, right? And another way to summarize the data is with the mean, which is very close to the maximum likelihood estimate. And you can ignore the standard error. Just forget this. Just look at the 95% credible interval, right? So this is what we will summarize. This is how we will summarize the data. Okay? And as I mentioned yesterday, this is different from, this credible interval is not the same thing as a confidence interval, because it's literally telling you the range of plausible values with 95% probability, given the data and the model, right? That's not what a confidence interval can give you. Although many people act as if the confidence interval gives you that information, it doesn't. It doesn't have any such meaning, right? So that's the big difference. All right, so that's how I would summarize the posterior. And notice that you can actually choose any interval. It's just because in frequentist statistics, we use 95% confidence intervals that I use the 95% credible interval. When I publish papers, I use these 95 intervals just because that's what people expect to see. But I could have chosen any interval. I could have chosen a 73% interval. It's up to you to decide what is a reasonable interval for you. And so you can use a quantile function to figure out whichever interval you want. So it's just a convention. One thing I should point out is that the 95% credible interval, the edges of the interval will be very unreliable estimates because they're based on very rare data, right? In the sampling, we will rarely get estimates in the edges of the distribution. Therefore, a 95% credible interval is not always a very accurate, right? And that's why Bayesians prefer to plot 80% credible intervals. They are based on much more solid estimates. So often you will see Bayesians plotting 80% intervals, right? So don't be surprised by that. That's the reason for it, right? Okay, so now let's get to the very exciting issue of sensitivity analysis now, right? So we had already fit quite a ridiculous prior, but let's try something even crazier. So let's try uniform prior for mu ranging from 0 to 5,000 and a uniform prior for sigma ranging from 0 to 500. So I've changed the priors now. Oh, sorry, I did not change the prior here. Let me fix that quickly. Just give me a second. I'm surprised that I made this mistake. Right, so I'm going to fit a uniform prior for both sigma and mu, right? So let's do that. Does this work? Oh no, I don't have BRMS set up. Right? BRMS, right? Let me run all the code that came earlier. Just a second. Run all chunks above. This should work. Right. Just give me a second to get this working so that I can give you the correct model. Yeah, so while this is going on, let's keep going. So let's pretend that this is a uniform. And so what I can do is I can fit the model with the new priors. Again, I'm using a Gaussian likelihood and I will get a new model posterior. So I can look at the posterior distribution and you will notice that it will not change much. We'll just take a look at it, okay? So I've got 168 mean for the intercept with a 165 to 171 credible interval, which is very similar to what we got earlier. And the standard deviations, mean and confidence interval has not changed much either, right? So this is a sensitivity analysis in action. What this is showing is that the posterior is not influenced that much by these priors that I have used. Right? This is how we do sensitivity analysis. Okay. Right. So as a general rule, we do not want our priors to have too much influence on the posterior. Yeah, usually that is true. We generally want to define uninformative priors. However, there can be cases where you want to use informative priors, right? And those cases would be when you have very little data, right? This can happen when you're working with individuals with aphasia, for example. So we might have only data from 6 or 7 subjects, right? But we might have a lot of prior knowledge from previous meta-analyses or something on that particular problem. So we could bring in informative priors there and build on what we know already. Another situation where I would use informative priors is when I have done a meta-analysis from previous studies. I could use that prior to decide how to analyze it. There's a question here from Masaki. If you want to stick to the 95% confidence interval for conventional reason or whatever, should we instead increase the iterations to gain more reliable estimates? Yes, you can do that, but nothing much is going to change because you will still get relatively rare, amount of data from the tails. But sure, you can increase the number of samples to 4,000 or something. The price you will pay is that it will take longer for the model to compile. That's also something you have to consider. You don't want to waste too much time fitting models, right? So that's important. Okay. So I will give you examples of informative priors later on, tomorrow or day after, right? But it's possible to use informative priors, but generally speaking, we won't use informative priors. Okay. So Yeah, so I don't need to discuss this. I think I already talked about all this. So now what I'm going to talk about in the last 15 minutes, right, is to show you a slightly more complicated linear model, right? So the model that I will look at is going to, so if you remember in our data, oh, here we go, right? So let me just quickly fit this model for you. I'm going to take uniform priors this time, right? On both mu and sigma. If I fit this model, right? So it's going to fit this. And if I look at the posterior, we'll just take a few seconds. Let's just wait. So look what Stan is doing. It's first compiling a Stan program, right? This is what BRMS is doing. It's first compiling a Stan program. It's writing it into Stan syntax. Then what it's doing is it's converting it into C code. Then the C code starts. And notice that 4 chains are starting in parallel, right? These 4 chains started in parallel. Where is it gone? Blah, blah, blah. Yeah, you see that? Each worker, this is one core, this is another core, another core, another core, right? They're all starting in parallel, and then it starts sampling, right? And initially notice that it's doing some warm up, and then it starts sampling, right? Each chain, and you can see that each of the chains is running in parallel. That's why you see sometimes chain 1 is mixed with chain 2. That's because 4 separate cores are printing out their information simultaneously, right? So you're getting all this information printing out. And then at the end, blah, 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 it's complaining about something that I don't want to talk about right now. But basically, this is, I've misspecified the model, but that's okay. I will deal with it later, right? So this is a secondary issue. But what I want to show you is that my posterior is not much changed. My mean is still on 68.67. Remember, the maximum likelihood estimate was 168.8 or something. And the credible interval has not changed, right? Similarly, the sigma posterior is also similar to the previous one. So that's a sensitivity analysis. We know, with these uninformative priors, we know that nothing much has changed. So we got pretty confident that we can report this result, and we are not getting a bias from the prior. Okay, so moving on to the next topic, I'm going to fit a model which will look at the effect of time of trial ID on reaction time, right? So it could happen that as Bruno keeps pressing his button, it could happen that as he goes down the experiment, he starts to get tired and he starts to slow down, or he might get better at, more fluent at button pressing and become faster and faster. So these are called adaptation effects, right? So we're going to look at adaptation effects as a function of by looking at the effect of trial, right? So what we have in the data is the reading times, but also the trial ID, right? So what we're going to do first is, if you look here, where's the, yeah, here, right? So if I say, right, if you look at the data, we've got trial ID here, and we've got the button pressing time here, right? So the first thing we're going to do is we're going to center the trial ID. That means we're going to take the df spacebar trial, right? And we're going to subtract from this the trial ID the mean of the trial ID. We're going to take the mean of this vector, right, and subtract it from the actual trial ID. So when I do that, what will happen is that the trial ID will now become centered, and that means that whenever the centered value is 0, let's see where, if I can find it here. Whenever the centered value is 0, this represents the average trial ID in the vector. That's what centering does, okay? Centering is a very useful thing to do. You should always do centering whenever you have a predictor, right, as a general rule. And so what that will do, when you center your data, right? So if you have some data Y, and you've got your intercept, which I'll call alpha, and you've got the slope, and you've got centered trial ID. The reason why it is very useful, well, one reason why it's very useful to center the predictor, right, is that when the trial ID is 0, this term will disappear, right, because it's multiplied with 0. And what you will get with alpha, what alpha represents then is the predicted reading time for the mean of the trial ID, right? Because when the trial ID is 0, that means it's the mean of the trial ID. And so this intercept now has a reasonable interpretation, right? It basically is giving you the predicted reading time or reaction time for the mean of the trial ID. This is actually very important in some situations. Suppose you're modeling the child's IQ as a function of the mother's IQ, okay? So the mother IQ could be the predictor, right? And if suppose you fit a model like this, simple linear model like this, then if you don't center the mother's IQ, then what is the meaning of this alpha parameter? The meaning of the alpha parameter is that when the mother's IQ is 0, the predicted IQ of the child is whatever, right? When will the mother's IQ be 0? That can't happen, right? So it would be a nonsensical meaning for the intercept. That's why we centered this. If we centered the mother's IQ, then the meaning of the alpha parameter is that when the mother's IQ is the average of the sample that you have, then the child's IQ is predicted to be alpha, right? So that's why that's one reason why it's super important to center the predictor. And we will center the predictor even if it's a categorical predictor. And that's what the sum coding is all about. We'll talk about that later. Okay. All right. So centering the model that we're going to fit is, so this is the centering procedure that I just told you, right? And so what I've got is a model that's going to model the reaction time as a function not only of the average reading time, but also of trial ID now. So I have a new parameter here, which I'm going to now define a prior for. So I've decided on a very vague prior for the beta parameter, which represents what? What does the beta parameter represent? It represents the predicted increase or decrease in reaction time when you go from trial ID, the average trial ID, to trial ID plus 1, right? That's what it tells me now. Okay. So, and all the other parameters are the same now. So when I fit this model, right, the beta is called the slope usually in our applications, right? So we can always check whether the priors make sense. We're using prior predictive checks, but I think we can skip that step. That's something you can try out yourself. So I've defined the priors. I fit the model in simply using the same syntax as in linear models, right? This is just a linear model right now with the actual data. And what I'm going to get as a result of this is I'm going to get 3 posterior distributions now, not 2, but 3. The alpha posterior, the beta posterior, and the sigma posterior, right? And so that's what I get here. I see that the posterior distribution, this is on the millisecond scale, this is on the millisecond scale, and on the millisecond scale, right? So what we are seeing here is that the millisecond values are very small. That means for every unit increase in trial ID, the predicted increase in reading time is 0.09 milliseconds. Okay, so the subject is slowing down slightly with every increase in trial ID. That's what's happening. Okay, so you can summarize this posterior. Usually we are only interested in this slope, right? The effect of the predictor. The intercept is of much less interest to us usually, and the sigma also, right? So we are looking at the posterior here, so you can summarize it pretty easily using this posterior sample. So nowadays, I think there's some new syntax for this, so you can look it up later on. It's not a big deal, but I get a posterior on the slope. Look at this, 0.09 with a 95% credible interval, right? This tells me everything that I need to know, right? So I could extract this information, the 95% credible interval, from the posterior or beta samples. And here, look, this is my summary for the paper. I would summarize this. I would not report the standard error here. You can ignore this. This is something irrelevant for us. The estimate and the credible intervals are the important thing. Okay. Posterior predictive checks. This can be done very easily in STAN. So what I'm doing here is that I've written a very simple command. I take the fitted model, right? And I'm producing simulated posterior predictive data, 100 simulated data sets. Those are those blue lines, right? This solid line is the actual observed data. And what I'm looking at is what the model predicts for future data. This is what I expect to see in terms of the distribution of the data under repeated, generation of posterior predictive data. So this is a good way to check whether your model is producing sensible data. If your model can't even produce data that looks like your observed data, then that is a very worrying situation, right? So sometimes you will encounter posterior predictive data that has nothing, that doesn't look anything like your observed data. That's a red flag. That means you have to go back and fix your model. Okay, we will encounter those situations.
I noticed that the posterior distribution seems to be somewhat a wider distribution than the actual data. In that figure, the actual data is a little bit more peaked distribution than the posterior data.
You're talking about this posterior predictive here, right? This here.
Yes. Yeah.
Yes.
Is that typical? Does that suggest that there's maybe something that we've missed in our model, or is that just sort of spurious, just by chance?
No, it's not spurious. So it's difficult to say whether this is a serious problem or it's just an artifact. Let's check this. Okay, this is an interesting question. This is very worthwhile to look. So let's see. I have this code here, and so let me first fit the model. Just give me a second. Here's my posterior samples, and here comes the model, right? So I first have to center my predictor. Should be done here, right? Centered the predictor. Then I define my priors. It should be coming up. Here come my priors, right? And then we're going to look at fit the model. Takes a few seconds. Then we are not going to plot the posterior, but we are going to do a posterior predictive check next, right? So here it comes. Here it is, right? Okay, so let's see. So suppose I set up the model. I don't limit it to just 100 samples. Let's say I want to look at all the samples. Okay, so I'll just do that. So let's get a picture about what the whole, posterior sample looks like. So here we go. Right, so can you see this?
Yes.
Right. So yeah, clearly there's something wrong here, right? So one thing that's happening is that I'm getting too fast data here, too much probability mass here, too much probability mass here, right? I don't get any of this tail. You see that I'm missing this tail? And the density plots of the posterior predictive data don't go as high as the observed data. And I sometimes get really low peaks here, right? So that suggests that I might need a better specification for the model. I think I can improve this model. The first thing I would try is to not use a Gaussian likelihood, but to use a log normal likelihood. That will already improve the model. Why? Because the log normal has a skew. It allows for a skew in the data. And so we will get a better posterior predictive distribution once we start including the skew, right? So we will improve on this model. So I think that this is not the best possible model we could have fit. Yes, I would conclude that from looking at this, right? So
Makes sense. Thank you.
Something more is needed. Yes.
Got it. Thank you.
Yeah, sure. So, okay. So let's go. Yeah. So the next thing we'll do is we try to improve this model by using a log normal likelihood. And so to understand the log normal likelihood, I've just written some code here. Actually, Bruno wrote this code. what we are doing is that we are generating log normal data. This RL norm function is generating log normal data with some mu parameter and some sigma parameter on the log scale. See that? Log of 6 milliseconds. Okay, the log, this is log 6 milliseconds. So what is log 6 milliseconds? I could exponentiate that value to find out the, the equivalent value in milliseconds, right? This is log milliseconds, this is milliseconds, right? So log, so 6 log milliseconds is 403 milliseconds, okay? And so these specifications for mu and sigma are on the log scale. I'm generating 100,000 data points from a log normal. And if I plot that distribution, you see this distribution. The log normal is producing data on the millisecond scale. Okay, the parameters are specified in the log normal scale, but it's producing data on the millisecond scale. And notice that the lower bound is 100. So this is a very realistic data set now, because there's this distinctive skew to the right that we see in reading time data, that we saw in our data as well, right? So this log normal likelihood seems like a much more sensible likelihood to use than the normal likelihood for reaction time data. Okay, so that's why I'm going to switch to the log normal. Okay, so you can look at all this later. It's not important right now. What's important is to realize that I have changed the likelihood function now. I made a radical shift actually, because, oh, sorry, this should not have been presses. This is trial, okay? Please, I'll fix this later. This is centered trial that I want to use here. So I've got reaction time as a function of the intercept and the slope with a sigma. All the parameters now, alpha, beta, and sigma, are now defined on the log millisecond scale. Please do not get confused, and do not forget to change the scale of these parameters, because this is the log normal now, right? So my parameter for beta is going to be a normal 0, 1. This is on the log millisecond scale. The sigma is going to be 0, 2, right? It could be a 0, 1 as well on the log millisecond scale, truncated, of course. And for the alpha, I'm using a normal 0, 10. Of course, this is a nonsensical prior, but it's fine. Okay, it's not, it's a very broad prior, but we can still use it and nothing bad is going to happen if we use it. Okay, so as I showed you earlier. So here I've defined the priors, right? Sorry, I've gone over time. Just please humor me for a minute. Let me finish this and then we can stop. So this is my log prior now. So I stick this into the model, right? Notice that I have centered trial here. I'll just fix that in the text. And when I fit the model, I get a posterior. And so look, who was it? Was it Scott who asked me this question? Yeah, right. So I'm getting slightly better fits now. So the model doesn't have those low peaks that I saw earlier, right? I've improved the fit a little bit, or improved the posterior predictive data rather, right? It looks a little bit better because it's taking the skew into account a little bit more, right? All right, so I think that.
Can I ask a question?
Yes, go ahead.
Do you have to log transform your priors, or could you just write them without transforming them at all?
See, the priors don't need any transformation. The priors are being defined here. Look, this, I have a normal distribution, but on the log scale. Do you see what I'm saying? So alpha is a parameter that is in the log normal distribution. This parameter is on the log scale, okay? But the prior on it is a normal prior, but the unit of this prior is now log milliseconds. I don't have to transform this at all, right? Because what is the statement that I'm making? Think about this. What statement am I making about the prior? I'm saying that the beta can be somewhere between -2 and +2 log milliseconds, right?
So you're using your knowledge about log milliseconds, right? Okay. Yes,
I'm using the fact that I know that log milliseconds is going to be generating data. So please humor me for a minute, okay? So let me just RL norm. okay? RL norm, if I produce 10 data points, okay, with a mean of 6 and a standard deviation of 0.5. Sorry, this is actually, so let's say 6 and standard deviation of 0.5, right? 0.5, these two numbers, 6 and 0.05, they're on the log millisecond scale, but the data I'm producing from the log normal is on the millisecond scale. Okay? The data will come out on the, that's a property of this distribution. So what I'm actually doing is that I'm using the log normal likelihood to produce simulated data now that has the right skew property that I'm interested in modeling. That's why the log normal is the appropriate thing, is an appropriate distribution. You could have used another distribution. You could use a gamma, you could use the gamma likelihood or an X Gaussian. These are also options. These are more advanced options we can think about later. Okay? But that's what's happening here. Yeah.
Okay, thank you.
Okay, so we can summarize the posterior, blah, 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 the usual situation, right? There's nothing special here. Here's my posterior predictive check here, slight improvement than before. And you can do the usual stuff again. The only thing that has changed in BRMS is that I've changed the family to log normal. And the other thing I've changed is that the priors are now on the log scale, but I'm still modeling the data on the millisecond scale. That's because the log normal likelihood produces the data on the millisecond scale, right? So that's what's happening here. So that's it. That's all I wanted to present to you. There's one paper that you guys should read at some point later on, not right now. It's about how to develop a Bayesian workflow for this kind of research, all this prior predictive and posterior predictive checks. And if you're fitting complex models with different kinds of contrast coding, you should read this article on how to specify the contrast coding. This is the important stuff for this lecture. There's one question here I see. If the posterior distribution of a parameter, for example, the slope includes 0, how to explain that? Let me get to that later, okay? That's a separate issue. Right now, all I want to achieve is to show you how to derive the posterior using sampling and how to plot and summarize the posterior. How to interpret it is a separate ball game, which we will discuss later, okay? So I will now stop. I'm sorry I went over time. I will pause the recording and we'll come back. Let's say I'll give you 30 minutes. So 11:40 we can start, right? Because I took 10 minutes extra. Okay, so we start at 11:40. See you. Okay, so I started recording again. We have 1 hour, 45 minutes or so now. And so I guess the best way to use this time would be to ask me questions, just free form at this moment. And if there aren't any questions, then maybe I can show you some example analyses from the homework exercises that I did not assign to you. So these are the options right now. So it's up to you to decide what you want. Any questions? Nothing? Everything's clear so far?
I'm having trouble getting everything set up to use RStan in R, but I don't know if that's within the scope of what we want to cover and talk about now.
Yeah, so why don't you tell me what kind of problems you're having?
Sure. So I know that you said to follow the installation instructions carefully. And so I went to the GitHub wiki page that you linked to, and then it says talks about how before installing RStan, you need to configure your R installation to be able to compile C++ code. And so then I downloaded the installer for Mac because that's what I'm on. And then I ran the installer and it seems to run okay. But then at the very end, it says like, there was a problem with this installation. It doesn't really explain anything else. So I'm a little bit stymied.
Which version of Mac are you using? Are you using the new M1 chip with Big Sur, or what's the operating system on Mac?
I am on Big Sur, yes.
And is this the M1 chip or is this the old chip?
It's the Intel one, which I think is the older one, right?
Okay, okay, I see. So can you show me what your error message looks like? Are you able
Sure.
to share?
Yeah, give me just a second.
Yeah.
I'm going to run it again and then get the error message. And then
Yeah, do I need to make it so that you can share your screen, or do you have that? Are you allowed to do that? Maybe you have to make you a co-host or something. Yeah. I made you a co-host, so maybe you can try sharing your screen.
yes. So I just get this rather unhelpful message that says it encountered an error that caused the installation to fail.
Yeah, yeah. So I think what you're trying to install is the tool chain here, right?
Yes. Yeah.
Yeah, yeah. I think that if I remember correctly, on the M1 chip, the tool chain will not install.
Okay.
And let me think. So how did I solve this problem?
But I don't think I'm on the M1 chip, right? That's the newest, right? I've had this for a couple of years.
Sorry. What I meant was that things have changed on the Big Sur as well. So
okay.
So we are installing. We are trying to install RStan, right? Is that correct?
Yes.
RStan.
Well, I'm trying to install the tool chain, and then install RStan.
No, hang on a second. I think I can recreate the workflows. So it says RStan getting started. So maybe I would like to share the screen now.
Sure.
So let me do this. RStan, where's the quick start? Okay, maybe this is the one, right? So let's see. Let's share the screen. All right, so so you do have the latest R version, right?
Yes,
4.0.
Yep, it's 4.1. I have.
That's good. That's fine. That's fine. And we strongly recommend that you use RStudio. Probably have the latest version of that as well. And so let's find out.
Double check.
What is this R toolchain compiler anyway? So what does it do? So, okay. And then open, double click. What does it contain?
So, Shravan, in the meantime, I found a thread of someone who went through the same error with the same situation. And so I'm gonna just copy in the chat the thread because there are some steps to follow. And actually, usually it's always the case that you have to, try to do several steps and see if that works or not. So maybe, yeah, maybe you should go through what the thread says. I mean, whoever is encountering this error, basically.
Yeah. So this is, Masaki Eguchi also has a message from some guy, compiler tools for CCP. Yeah, that could be relevant. Yeah.
Okay.
And Paula, yeah.
I will check those out and do those.
Yeah, I remember. So I do remember vaguely that I had the same problem with this toolchain thing, and it has something to do with Big Sur. And then what I did, if I remember correctly, is that I actually checked what the toolchain does, and I did it by hand. So
Okay.
that's how I solved that problem. But it seems that this guy, the coatless professor, has a blog which explains how to install. It's an interesting question. Just a minute.
Yeah, so actually in the thread I was sending, that's the answer with the solution. So definitely that's the link you should have a look at.
Okay. Yeah.
Will do. Thank you.
So I guess this is the solution installer package for macOS. Okay, I see.
It's exactly the same error.
I'm curious to know what the solution is. I just want to see.
No, that's not the solution. Go lower, lower. Yeah, that's the solution in the link.
Who, this guy Jeff altogether or what?
Yeah, but he says he's following the instructions on that link, and that link is the one the other participant sent around. So
yeah, see, it says run through the steps that the installer does automatically. So that's what I also did. Follow the instructions from the codeless professor. That's what Masaki Yaguchi also pointed to, right? The same issue. So yeah. This is the solution. Yes, I had exactly the same issue.
it's unfortunate because every single new version of Mac causes some different problems, and then I mean, I didn't update to the new one precisely because I know it would break again the stuff, but it's very unfortunate that every update generates new problems.
I'll follow those instructions.
Yeah.
Thank you.
Yeah, it's pretty straightforward, I think. I remember now that I had to install G-Fortran myself manually, like this guy says, over here. Yeah, I remember all this now. I should have written it down somewhere. I'm just too lazy. But yeah, okay. So this is certainly a problem that everybody faces, when they are setting up RScan. But if you don't have this working, the problem is that you won't be able to do anything that we have assigned. So this is a critical problem that you should be able to install it. Okay, but it's doable. I have also faced this problem. So any other questions, any other issues that people have they want to talk about? Okay, so if not, then I'll talk about a couple of things here. So I think I had, yeah, this is a good exercise. I think this one is a very instructive exercise. Oh no, is this the one I wanted to talk about? No, I wanted to talk about power posing actually. So let's see which one is the power posing. Yeah, this is a great exercise. Let's do this one, okay? So this is a very special problem because in this particular research problem, I happen to know absolutely nothing about the problem. I have no expertise whatsoever, right? So it's a good example of how to start with such an issue. So the research problem involves a simple linear regression, right? And I don't know if you guys are all familiar with this famous paper. This is a paper on power posing and testosterone levels. Do you know this, right? So there's a very famous TED talk that was given in which the researcher claimed that, before a job interview, what you should do is stand in front of a mirror like this, in a power pose for 2 minutes. And what that will do is that it will increase the testosterone level in your body and lead you to perform much better, in the job interview and so on. And the claim in the TED Talk, which has been viewed something like 36 million times or something, was that the testosterone level goes up after the power pose, as opposed to, you know, if you have a low power pose or something. I think a low power pose is something like to stand like this or something like that. And so you have a condition where you have a high power pose or a low power pose. So that's what you're seeing here. You're either in the high power treatment or the low power treatment. So this is a between subjects setup, okay? So each subject is given either a high power treatment or low power treatment. And this is the subject ID. And what they have is the testosterone level measured before and after the treatment, okay, which can be higher or lower. So it's a pretty simple setup. It's a simple linear regression. And there are 39 subjects, right? And what we want to know is whether high power pose will lead to a greater increase in the testosterone level, you know, after the treatment has been done compared to low power pose. So basically one way to do this would be to compute the difference, you know, in the testosterone level before and after. So that gives you the change in the testosterone level in the high power and the low power conditions for each person. So you could create a new column here with the difference in the testosterone levels from here to here, right? For each of these things. Is the setup clear? Data is pretty clear, right? So the research hypothesis is that on average, assigning a subject with a high power pose versus a low power pose will lead to higher testosterone levels after treatment. So the way they were measuring this, I think, was through the saliva. So they would just take a stick, put it in the mouth, measure the testosterone level. So I've been told by experts that that's not a very accurate measurement. So there's probably a lot of measurement error in that kind of setup. So, but nevertheless, let's just treat the data as valid. Okay. So we have to estimate this change in testosterone due to high and low power. So that's the exercise. Okay. So let's look at my solution. So I came up with a solution. So these people released their data, which was really nice, which made it possible to actually do this analysis. So here it is, right? Power pose. Where is it? Where's my power pose data? Here, right? So yeah, so this is in the data set, you know, in the library bcogSci. I just load the data. This is just the data I just showed you. And then what I did was I created a new column. Can you see this? This is line 646, right? So this is line 646 here, right? I've created a column called change, which is the change in testosterone after and minus. So after minus before. That's how this is done, right? So I've got a new column now, which is the change column. Let me just plot this, right? So you see a new change column here, right? So this change column here, in this case, subject 29 showed an increase. Subject 30, who was given the low power, showed a decrease, right? Then you've got subject 31 with a decrease. So, and subject 32 with an increase. So there's a lot of variation going on here, right? You can see that. All right. So let's take a look. Let me close this chat. So you know, a really simple model would be something like this. A simple linear model, okay, would be something like this. LM change and HP treat. HP treat is the column that actually encodes high versus low here, right? And so we have data frame power pose, right? So I could fit such a model. And if I summarize this is the frequentist model. If I fit this model, what I get is the estimate of testosterone levels when the treatment is low, and when the treatment is high. Okay, this is when it's high, right? And when the treatment is low, there's a decrease in the testosterone level. That means With high treatment, you get an increase. But the effect is not significant here. You see that? It's not a significant effect. So we're going to do this analysis in the Bayesian framework now. And the first thing that I tried, notice that I just wrote the same command as in the linear model. I did not define any prior. How could that be? How could I fit a linear model in BRMS without any prior specification? Can you guess?
BRMS default priors?
Yes, this is because BRMS does something extremely dangerous. I don't really like this kind of thing. So what they have done is they've tried to make it easy for the modeler by trying to figure out some default priors for the data that you have, right? So in theory, this will work. So let me try this. When I run this model, it's got some implicit priors and implicit settings that will set up all the relevant, priors. But whether they make sense or not, we don't know now. We are just now leaving it to the software, just like in the old days with the frequentist paradigm. We are leaving it to the software to figure out whether this is a sensible model or not. This is not a very good way to proceed. So, but anyway, let's just do it anyway. Right? And so you can also, once you fit the model, so the model is now fit, you see that there are no warnings. See that? There's no warnings. That means the model actually converged and everything. So I could, if I look at the summary output from this model, what it tells me is what the intercept, notice that it's very similar to the intercept that I had with the frequentist model, and quite similar estimate for the low treatment, right? And I get a 95% credible interval here. That's mostly negative. The posterior is mostly negative, slightly a few positive values here, okay? And this will now, this also allows me to talk about the question that came at the very end of the last lecture about how to interpret the posterior if 0 is included in it. This is what I'll talk about now, okay? But let's first try to fit this model. So one other thing to notice is that the sigma parameter is 20 with an uncertainty of 16 to 26, right? So if I were reporting this result, I would say the effect of treatment is -9. So that means low power pose will reduce testosterone on average by -29 with a credible interval of -22 to 3, right? And the standard deviation I would report with the credible interval, right? That's what I would report there, okay? Okay. So one interesting question now is, what are the priors that BRMS used? Well, we can look at those, right? You have prior summary command. I hope it still works. Let's see. Yeah, it prints out the priors that the system figured out for us. So what the author of BRMS did is that they defined some flat prior on the intercept and some flat prior on the slope, right? It doesn't even tell you what it is. I don't know what this prior is, actually. It doesn't tell me. Maybe it's an improper prior, which I'll just explain. And for the, oh no, here it is, sorry. I'm mistaken here. So the prior is a student T prior with 3 degrees of freedom and some mean and some standard deviation. I think these are the parameters in this thing. But the important thing is this 3 degrees of freedom here, right? What this does is that it creates an approximately a Gaussian distribution with fatter tails. That's what a 3 degrees of freedom prior does, right? And for sigma also, they have a similar prior, which is probably a truncated T distribution, again with 3 degrees of freedom. So the low degrees of freedom are intended to allow extreme values, right? That's one way to fit this model. So actually, so even though I'm criticizing this whole setup for having default priors, actually I'm in the very awkward position of knowing nothing about testosterone. I have absolutely no idea what I'm doing here because I've never worked on that kind of data. So if I were really analyzing this data, I might actually be willing to live with the default priors. But, you know, this situation you will almost never be facing, because when you do your own research, you're likely to be an expert in your own area. So in your area, you will be able to figure out what a reasonable prior is. Of course, we'll get some practice on that later, but I'm just saying that this is a very weird situation to be in, where you don't know anything about your problem, right? Of course, this can happen to you when you're a consultant, if you're working as a consultant, you know, for a clinical trial or something in some medicine area where you're not an expert, right? So typically what statisticians do when they work as consultants, you know, for medical researchers, they try to learn something about the area before they actually do any statistical analysis. So it's very rare to be a consultant in a problem where you know literally nothing about a problem. Working blind like this will probably lead to chaos later on. So, so you can also extract the priors from this model by using this get prior command. Earlier we saw the prior summary. You can use the get prior command, and this shows you that the system, these are the same priors again. So you don't get any new information here. It's just another way to plot, to display the priors that are set up, okay? So now the interesting question is, there's no way for me to proceed. I can't actually use informative priors here. So for now, I'm willing to just stay with this, right? So let me see, how would I summarize this? How would I summarize this graphically? So can I do stand plot, fit, power pose, something like this? Can I do that? Yeah, so this is one way that the model, that the software will print out these posteriors, right? So you're looking at an 80%, can you see this? 80% credible intervals. These are the thick lines. And the 95% credible intervals are shown here, right? So with these thin lines here. So this is also one way to summarize the posterior, right? Another way would be to use, I think, MC plot or something. Let's see. Oh, I see. MC plot does this too. If I say, how do I get a histogram? Whew, I can't remember this. Just a minute. Intervals type, I think it's type, right? Hist, yeah, okay. So type hist. This should give me a histogram. Yeah, so these are the three things that I see, right? So now the 95 credible interval for this slope actually is contains the 0 point, right? And so the question is, how would you interpret this, right? So given our frequentist training, we are trained to think of a significance test, right? It's a very instinctive reaction to try to think of the significance of this effect. Is it significant or not? And the way people, you know, use Bayesian analysis is often to ask this kind of question too. By just looking at the confidence interval, what they notice is that the interval contains 0. Therefore, they'll say that the effect is non-significant, even in a Bayesian analysis. But so here's the problem, okay? So the first problem is that, as I mentioned earlier, the edges of the 95% confidence interval are not going to be super precise, because you can see that there are very few samples here, right? The second problem will be that if I were to rerun this experiment repeatedly, I would get slight deviations, you know, in the credible interval. It would just keep changing slightly, right? Or maybe quite a lot, I don't know. And so the fact that 0 is not contained or 0 is contained within the interval is actually not a super interesting fact per se. It's not telling me anything about the real world. Not necessarily. I mean, it could be, of course, but it's not necessarily telling me anything. And the reason for that is that let me come back to my, right? So as scientists, the key inferential tool that we should rely on, yeah, is replicability. right? So suppose I'm looking at the effect of testosterone, this particular example that I'm talking about. What I would want to know is that if I replicate the experiment multiple times, right? If this is a zero line, let's say, right? And so suppose I'm getting in my first experiment, I get something like this. In my second experiment, I get something like this. Third replication attempt, I get something like this, you know, or something like this, right? So what is more important to notice here is the relative consistency of the effect, right? In this particular example that I'm showing you, I'm consistently seeing a tendency going in the negative direction here. So most of these effects are not significant, right? So, but is that informative or not informative? I would say that whether the effect is significant or non-significant is completely uninformative. What is more informative is the consistency of the pattern under a repeated sample. So one thing that I would do in such a situation is that if I have multiple such experiments, I could pool the data in a meta-analysis, right? In a meta-analysis, and try to find out if for all the studies, can I get a estimate that gives me a pretty tight estimate of the effect or not. So this is something that I do all the time in my research. And so let me see if I can find you guys an example. So just one second, I'll just pull up one of my talks, one of my recent talks. So let's see. Maybe this talk, I gave a talk in Stanford some time back, and so maybe this one has what I want. Just a minute, let me just pull up something. Right, yes, this is a good example. Okay, so what I'm showing you here is 1, 2, where is it? 13 or so studies, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 studies, right? And so what is really interesting about this data, these are data sets published by different people. This is a data set that I created, which was a direct replication attempt of this data set here. So notice that this original study number 1 here, this was done with 40 subjects. I reran this study with 181 subjects. Look at the interesting difference in the posterior estimate here. This one is, if I did a frequentist analysis, this would be a significant effect because 0 is not contained in it. But in my study here, which is a direct replication attempt of this study, the effect actually contains 0. Do you see that? 0 line is here. My sample size is much larger and my posterior distribution contains 0. So what the frequentist would say here is that this effect is informative and this effect is non-informative. But actually it's the other way around. This effect is completely uninformative because of the large confidence interval, the large credible interval here. This effect has a much tighter interval, and even though 0 is contained in it, the estimate is tight and the effect is still negative. This is what the theory predicts, okay? So the effect is negative. And this dark bar that you see is a result of combining all these estimates, including their uncertainties, just credible intervals. I include that uncertainty in the analysis and I compute this posterior distribution of the overall effect. And you can see that this is a pretty tight credible interval. This is the theoretically predicted effect. And notice this is the computational model. The model actually predicts this range of effects. This is the model's predictions. This is a computational model predicting these effects. This is the observed data, and it lands inside the predicted range. So this prediction of the model is validated by both this data and this data, even though this one is a significant effect and this is a non-significant effect. So what I'm trying to say to you is that you should try to interpret the posterior distribution in the context of what you know about your problem, right? So what do I know about my problem? I have a theoretical prediction. I have other data sets out there that I can pool together to compute a posterior distribution using a meta-analysis, and that gives me much more information. So what you should not do is try to interpret the this posterior distribution by checking if 0 is in the credible interval or not. That is not a sensible thing to do because of the inherent variability of data under repeated, replication terms. You can see that right here. This is real data. See how much variation there is in this data, right? So that's a very important lesson here. Any questions on this point? Is clear?
But then, sorry, I'm trying to think it through and formulate a sensible question. But I guess my question is, then it doesn't really matter what the inclusion of 0 is not informative. But then this makes sense for when we have results from multiple sources, like we have multiple studies and we're pooling over them.
Right.
But what if it's an individual study? How would we interpret the interval then?
Yes, that's exactly the right question to ask now. So now you have to ask yourself, what is the goal of a data analysis, right? So one possible goal can be, and that's what I've been trying to teach you, is to obtain a posterior distribution of the target parameter of interest, like the slope or something, and then try to interpret it in the context of what you know and what your theory predicts. That's one way. The other way is the way that, is standard in psychology, which is to ask, do we have evidence for an effect or not? That's the kind of question you are asking implicitly, right, Maria? That's what you want to know. From what, what you want to know from your one particular study is, do I have evidence for an effect or not? You don't really care what the mean is. You don't care how much uncertainty there is. You just want to know if there's evidence or not, right? Now, to deal with that kind of question, you do need to do some model comparison using something like Bayes factors. Okay, so that is a methodology that I will teach you tomorrow or day after, right? Day after is my plan for that. And I can give you a quick preview on how I would do that. Okay, so what I would do is,
I guess I'm more interested in what is the alternative, because I get the general idea, like the idea of interpreting the posterior, but I get it on the statistical level, not on the theoretical level, I think.
So what is the alternative, did you say?
Yeah, I mean, how do we, so the
way
is evidence for an effect, but then the alternative is interpreting the posterior distribution. But how would that look on the theoretical level?
Right.
Like in the discussion part of the paper.
So the question you're asking is like, how shall I carry out inference after I have fit the model? I need to carry out some inference, and what shall I do? So here are your options. Okay, these are all the options available to you. So first we have the frequentist approach, and on the right hand side I'll write the Bayesian approach, right? Bayesian approaches, actually there's more than one, right? So the classical frequentist approach is to carry out something called a likelihood ratio test. This you guys must be familiar with, right? This is the ANOVA. ANOVA, right? So for example, if I go back to my toy example here, where is it gone? This PowerPoint gone, sorry. 600. What is this? Oh, these are the solutions, sorry. Where was I? Here, right? So let me fit this model again. Right. So if I fit a full model, I have LM change as a function of HP treat in the DF power post data. So what I would do in the frequentist paradigm is that I would create a null model, right? Where I would have no effect as a predictor. So just the intercept. So I would write something like this, right? And then I fit these two models, and then I say likelihood ratio test, M full, M null, right? That's written in the ANOVA function here, right? That gives you the likelihood ratio test. And then what I do is I check if my F score is significant. It's not significant. So I fail to reject the null hypothesis. Oh, what's happened here? Why is the degrees of freedom 1? Oh, it's the order in which I put it. Sorry. I should have put the null model first and the full model later. Right? So that's much better. So I've got the model with 1 extra degree of freedom low down here, and then I see no significant effect, right? So that's how I would do it in the frequentist paradigm. So that's what the logic there in the frequentist paradigm is basically comes from the idea that to compare two models, you have to look for the relative log likelihoods of those two models and decide to choose the model with the higher log likelihood. That's the idea. So evidence, the word evidence has a special meaning in statistics, and that has to do with the likelihood of each model, compared to some baseline, of a model compared to a baseline model. So that's the frequentist approach, right? In the Bayesian approach, so there's different, oops, wow. These people have over-engineered the software to an extent that it doesn't make any sense anymore. So now it's frozen. Sorry, I don't know what's happened here.
I think it's just lagging. Yeah.
It's really annoying. Right, so the options that we have in the Bayesian framework, one option is to just say that I'm just going to do estimation. No model comparison at all. I will just plot the posterior and try to interpret it, okay? So how would I do such an interpretation? Well, one way to do that is to use something called a region of practical equivalence approach. Right, so what I'm saying here is that after I've done my estimation, I want to make some decision about my research problem. So how do I make that decision? I make that decision by plotting my credible interval of the posterior against some predicted interval, right? So my predicted interval could be this one. So my theory says that the interval should look like this, okay? And my data give me such an interval from the model, right? So what can happen is that you can have the following situations. Either the data and the theoretical prediction match up perfectly, like I'm showing you right now, or you could have a slight overlap, or you could have an overlap in this direction, or you could get data that fall completely outside the predicted range. So these cases here, these have falsified your theoretical prediction, right? And these cases here, this one and this one, these are ambiguous. They kind of overlap with the predicted region, but they don't actually give you conclusive evidence, right? This region here is completely consistent with the theoretical prediction. Now, there's actually more possibilities. One possibility is that the data actually lands much more tightly in a large sample study inside the theoretical region. That's what actually happened in this study that I'm showing you. The theoretical range is here, and the predicted range, so the observed range from the meta-analysis lies inside the observed range, right? So I can actually argue that I have evidence for this effect based on this approach. This is called the rope approach, region of practical equivalence. This is the approach that I use in my research because I usually have solid theoretical predictions from a computational model. I'm looking at real predictions that I can test against. Now, there are other situations where you do not have a solid predicted range. All you have is a prediction from a hand-waving theory. Most of the theories in sentence processing, for example, are just hand-waving theories that something will happen, that you will have more difficulty. Will it be 10 milliseconds or 2000 milliseconds? The theory has nothing to say about that, right? Because it's a paper pencil theory. So in that situation, you're asking a question like, is the effect present or absent? This is the kind of question that you see most often in psychology and psycholinguistics. So in that situation, if you're looking for evidence for an effect, then you're going to have to do something similar to the likelihood ratio test, and that will be the Bayes factor test, Bayes factor analysis, right? That's one way to deal with this problem. And it's very similar, the Bayes factor is very similar to the analysis of variance that I just discussed earlier, right? It has some superior properties because the Bayes factor will be comparing models taking into account the uncertainty of the parameters in the models. The ANOVA cannot do that. The frequentist ANOVA doesn't do that. It doesn't take the uncertainty of the slope into account. That is a critical difference, okay? So we will get to the Bayes factor on Friday, and I'll show you how to do this. Another way to look for evidence is to use something like k-fold cross-validation. So what you can do is you can set up two alternative models and fit each of those models on a subset of the data, and then check the prediction of the model for the remaining data and compare the distance between the prediction and the actual held out data, right? And the model that is closest to the held out data is the winning model. Right? That's one approach that we use. If you look at Paula Lisson's work on her homepage, she probably has her papers there. That's one approach that she has used for model comparison, right? So these are the options that you have. In the textbook, we have a chapter on k-fold cross-validation. I won't cover it in this course, but it's there. But I will talk a little bit about Bayes factor on Friday. So by the end of this course, you will have a good idea of good understanding of how to use estimation and the region of practical equivalence. Well, that I've already explained now, and the Bayes factor for deciding, for figuring out what to conclude from the posterior distribution, right? That's an important thing. Now, one thing I want to add here is that when I actually publish my papers, what I do is that I try to avoid doing a Bayes factor analysis, right? And there are reasons for that, which I will discuss on Friday. But the way I report my results are pretty straightforward. I will show you that I have successfully managed to publish in, our top journal. At least in my field, it's the top journal, so Journal of Memory and Language. I have published papers like this in which I haven't done a single statistical test, right? So in this paper, I report 7 experiments, and all I do, I'll show you. This is a published paper. It's unbelievable, right? There's not a single significance test in this paper, but I got away with it. So all I do is I report the posterior distributions, and I try to interpret them in the light of some previous data that we have, right? So it's possible to, reason about your data in this way, in the light of what is claimed in the literature and what the expected range of effects might be. So this is kind of this is sort of a region of practical equivalence approach, right? So you can see that this is what the original study found, and my replication attempts, these are my replication attempts of this study. I don't find similar patterns at all. I think you would agree with that. And then let me show you, oh, sorry, again, I'm switched to Japanese for some reason. So I did more experiments in this paper, and I report the results in a very similar way again, right? So here again, what you see is this is the original data set, right? The original reported effect, and these are my replication attempts. So you can see that my attempts are landing inside the original study, but with tighter intervals, right? And so this last study here has 100 subjects. This original study had 28 subjects. This was published in JML, this original result. But my estimate is much tighter, and it lands in the mean is very different and the interval is much tighter. So this is a more informative effect than this one. And notice that this is not significant, but mine would be statistically significant. But that's not the important point. The important point is that the interval is very tight and the estimate is very accurate here, right? In some sense, right? So similarly here, again, this is the original study. These are my replication attempts. And in this original paper, they claimed an interaction, right? Implicitly, they claimed an interaction. That's the interaction there. Here's my large sample replication attempt of that interaction, centered on 0, basically, right? So you can see that you can evaluate data without actually doing these kinds of formal ANOVAs and stuff like that. It's possible to do this. It's possible to interpret the data. I think that the key to doing this kind of, interpretation of the posterior by just looking at the posterior is that you should have replications of that data if possible. So I could afford to do this. You may not be afford to do this. You may not be able to do this. So what I would suggest is that if the reviewers demand that you provide evidence for or against an effect, then just do a base factor analysis just to make them happy. I do that sometimes when my reviewers insist on it, and I would show you how to do that on Friday. So that's I think the main issue that I wanted to get across to you, that it's possible to talk about data in terms of the posterior distribution. Statisticians are much more comfortable doing this than people in psychology and psycholinguistics, but I think that culture will change slowly. Any other questions?
A very short question about the K-fold cross-validations. So which metrics is usually used for K-fold cross-validations to do this hypothesis testing? Is this the BSE or something like this?
No. So we just basically what we do is that we will compute the average distance between the predicted and the held out data. And that's called, that measure is called deviance. So we use a measure of deviance to figure out how well the model fit goes. And we will compare the model fit, in terms of deviance for the two competing models, and the model with the lower deviance is the one that we will choose, right? So there are full details on this in the textbook. So there's a chapter on this. You should read that, okay? Take a look at this. And so somebody's asking me for a reference for this paper that we published in JML. The reference is this here. See that? The statistical significance filter leads to over-optimistic expectations of replicability. So I'll give you the full reference from my homepage, right? So if you go to my homepage, I'll show you. Actually, I have many papers like this. This is not the only one. Okay? So I'll just point you to these relevant papers. The paper that I just mentioned is this one here. You can download it from the JML homepage. This one you should look at. This is a very instructive paper. And another paper I would advise you to look at. I've just published that like last year, was it? I don't remember now. Yeah, this paper, right? Also in JML. This paper tries to replicate a small sample study that was published in JML with a much larger sample size. So in this paper by Lena Yeager et al., we took our time to collect the data. So we collected 181 subjects where the original study had 40 subjects. And it took us 4 years to collect this data. Just one experiment, very large sample size, right? And so again, you will see that we are just using the posterior distribution here to interpret the results in the light of the previous study that investigated the same issue, okay? And in this paper, one of the reviewers insisted on seeing, whether there was evidence for an effect. So we did a Bayes factor analysis. So that's also discussed over there. And all the source code for these things are available for these papers. So you can just rerun all the analyses that are over here. You can try them out yourself with the data. Okay? So you can retrace our steps in this paper. I put all my data and code online. You see that? All my data and code is always online. So you can, this one doesn't have any data, or maybe it does. Yeah, it does. So the link is inside there. I'll fix it just now. But you see that all my papers here all have code and data available, right? And when the code doesn't show up, it's inside the paper, and the link is inside the paper. So you will always find the code and data. Yeah, that's a very good practice, by the way. I think Anna will explain this to us, I think either today or some other day. She will
on
explain,
Friday.
Oh, on Friday, right. Anna will explain on Friday how you can set up a nice reproducible workflow, right? So that other people can also retrace your steps and maybe modify analyses and look at your data differently. Right? It's a very good thing to provide that kind of capability to your reader. When I review papers for journals, I insist on seeing the data and the code, and I often reanalyze the data of the authors to check if the analysis makes sense or not. Right? That takes more time, but it adds a lot of value. I've often found problems in other people's analyses, and other people have found problems in my analyses, right? So this paper actually, this had a horrible mistake in the analysis, in the review stage. And one of the reviewers checked our code and found the mistake. So we fixed the error before we published that paper. That is very, very useful. I mean, imagine the embarrassment of publishing an incorrect analysis in JML. So I think this is you should never be afraid to let other people see your data. What's the worst that can happen? You make a mistake, but I don't know anybody, including myself, who has not made mistakes in their life. So this is not a big deal, right? All of us make mistakes, and you should just be completely okay with that. It's just human to make mistakes, and nobody's going to hold your feet to the fire for that reason. Okay.
If I may add to that, I've heard about lots of cases reported by our colleague Titus von der Maisburg, who also checks the code of the papers he reviews. And he says that he often finds mistakes that actually when he fixes them, there is more evidence for the hypothesis that our authors wanted to test, or for the main point that the authors wanted to make. So people are usually afraid that a mistake will completely destroy their beautiful theory, but actually some mistakes when fixed support your theory even more. So it's very useful to have them fixed.
Absolutely. Yes, it can go in the other direction. So it can be a positive contribution also, right? To find effects. Yeah. Yes. Okay. Are we good for now? Oh, great. Scott just informed us that the method works. We need to put this up on the web somewhere, because, or maybe I will inform the Stan people to do something about this and put it on their homepage. I will just tell them to do it. Okay? So the Stan developers can update their homepage and fix this so that people don't have to go searching on the internet for this. Thank you, Scott, for letting us know. That's great. Okay, so we're all set.
Thanks for the help.
Yes, great. I'm glad that it worked out. And thanks to Masaki and who was it? Paula, I think, right? Who pointed out all the websites. So now you guys can take a break for lunch, I guess, right? Am I right? It's a lunch break now, right? Or for some of you, it's the middle of the night. And then you'll do your homework now. And then Anna will take over today. Is that right, Anna?
Yes, that's right.
Yeah. So my network doesn't work very well in the, during the dialysis center. So I will stay away from the internet in the afternoon. Okay. So don't expect me there. Okay. So you won't see me anymore today. I'll see you guys tomorrow. You can of course keep posting messages on Slack, and I will keep looking there and try to answer if I can. And in any case, by tomorrow, I will have answered most of the questions. So I'll see you guys tomorrow. And tomorrow's plan is the following. So I've finished this chapter now. Chapter 3 is done. Oh, sorry, chapter 4 already. Are we on chapter 4? Yes, right? I've forgotten now. Where are we? Yeah, so, no, did I get this right? Have I messed up all this?
I think you just used one of the exercises from chapter 4, but we haven't seen the actual content for chapter 4.
Oh, yeah, that's right. Yeah, so I'm going a little bit faster than the chapters because what you're supposed to be doing right now is chapter 3, I think, right? It's the third day. But what chapter 3 does is that it just introduces the linear modeling framework, which I already showed you today. And so what's happening today, what your job today is to fit these simple models, with button pressing, the button pressing model, and look at the effect of priors and all that, right? Just by having more informative priors or less informative priors, the log normal likelihood I introduced today, right? And that's pretty much it, right? That's the first one. So this Bayesian regression model stuff is also just a continuation of what we did today, right? So you can also start looking at it. This logistic regression stuff I will introduce quickly tomorrow because we don't have time today. And then we will move on to talking about hierarchical modeling. So this is a pretty complicated chapter. So I want to get started tomorrow on this. And then if I can finish this chapter by tomorrow, I will talk a little bit more about prior elicitation. This is both an art and a science. That's why the title of this chapter is Art and Science. And finally, I will jump ahead a little bit and give you a quick entry into Bayes factors. Where is Bayes factors? Somewhere coming up. Meta-analysis. Yeah, this chapter, you don't have to read it, but I will give you a quick overview of Bayes factor analysis to give you basic functionality, basic ability to use this tool for model evaluation, right? So that's basically the plan for the rest of the course. Okay, so unless there are more questions, I'm going to now stop recording. So see you guys tomorrow. Bye.
Bye. Thank you.
Thank you.